So can you imagine you have all these 2.5 mm cables? There may be 37 wires, 37 cores in a typical pilot wire. So you have 37 wires running between substation A to substation B. And where does it go through? It goes through the roads. And what happens with roads? Excavation and all sorts of things. And so what happens? The wires will fail. I can tell you there was a project in the East Coast. We even put in two cables. So two cables, each one 37 wires, should be very safe, right? Guess what happened? They both fail. And these wires are very small, it's very difficult to detect faults. So in the end, give up. The relays are there, but cannot be used. And my understanding is with optical fibers, the reliability is much better. Of course, it can also be used for other things. So my impression was, wow, pilot wire, good old technology, but no longer in use.
Good morning, Mr. Lee.
Good morning.
Mr. Lee, are you there?
Yes, who's there, please? Is there a problem? Sorry, is there a problem? Win, is there a problem?
No, I think he muted it. Okay.
Oh, I see. Okay. So where was I? Yeah. So my guess was pilot wires with the availability of optical fibers and with the unreliability of the pilot wire itself, what happened? Probably nobody used it. But to my surprise, after the calls, after the last Saturday, I got a few calls. The first came from Chua Tiong-Siang, my old colleague. And he said, hey, you were wrong. We still use them. And then another guy said, oh, we are still buying a lot of this for projects. So sorry, I had to correct myself, and I had to go back to something which I didn't want to talk about. So that was what happened. The other thing that I did was I sent to use a wiring diagram for a bus bar protection for a double bus bar. So I'll come to that later. So this morning, very quickly, I'll go through a few of the points that I have missed. Then I will then, of course, continue. I won't revise whatever we have done. Then I will go through the notes. So what are we going to talk about today? Essentially, we're going to talk about main and backup protections. We're going to talk about breaker failure protection. We're going to talk about bus separation scheme. And finally, we're going to talk about auto reclose of lines. And that's before we go on to talk about the last topic. And that will be on testing of protection relays. I had wanted to go into the history of some of the protection relays, but I don't have enough time, so I will skip that. Okay, let us see what we had promised you in the flyer. You hold on, I got to check something. Hold on. I'm trying to do my antigen test, and I think the procedure that is there is still wrong. So that was a timer telling me to check the results. So okay, I'm having a problem. So after this, I got to do it separately. As I said, the test instructions are very confusing and conflicting. And so if any of you want to go and buy one of these test kits, you bet at the pharmacy itself, you better open up the box and ask them exactly what happened or how to do the test. Okay, that's mine. And I probably will have to do it slightly differently after this. Okay, so where are we? So of course, today we are going to talk about protection of transmission systems and testing of protection relays. I've talked to you about protection philosophy. I also talked to you about the importance of city location, about current and pilot wire protection. We have talked about distance relays, and we have finally talked about bus stop protection. That was the whole of last week. So today we're going to talk about the backup protection for transmission lines, transmission systems, And you find that the backup protection for transmission system is completely different. Essentially, for lines and bus bars, the three components, main components are in transmission system. If you're not in a power station, are your bus bars, your lines, your transformers. And out of that, two of them don't have any overcurrent relay. We don't use overcurrent fault relays, except for the directional relay. Directional fault, that's a different application. So here we're talking about backup. So we don't use the overcurrent fault relays in transmission systems. And so what do we use? Our main reliance is on a distance relay. So the distance relay is a backup for transmission lines and also for transmission bus bars. It also provides some degree of backup protection for transformers, but it doesn't protect the whole transformer. But I'll show you later on today. Transmission, this distance relay is not very good at doing the job because of other limitations. So although we say, we got a backup, it doesn't provide the backup the same way that overcurrent relay does. And we don't use overcurrent relays because there's so many complications using overcurrent relays. The only time we use overcurrent relays will be for the HV side of the transformer. That's where the overcurrent protection relay starts. So we are going to talk about how we use a distance relay as a backup protection for transmission lines and bus bars. Okay, but it only protects it protects 100% of the next line, of the first line, of its own line. But for the next line, it doesn't do a very good job. But it gives very good protection for the downstream bus bar. So we'll talk about this today, okay? And then there are others, we have breaker failures and so on. So the distance relay is probably the most widely used transmission backup protection, but it has its own failings, okay? Why? Because although zone 2 it covers more than 100% of the line, it doesn't go very far beyond that line. So it only can protect you if the fault is in the first part of the next line, not as a backup protection. Yes, it works. But if the fault is at the other end of the next line, it doesn't work, because it will depend upon zone 3. And zone 3 is too slow. So forget about zone 3. So, and that's why it says here, long time delay of zone 3 makes it ineffective as a backup. If the zone 3 ever has to operate, probably the system will have collapsed first. Then we're going to talk about breaker failure. And we're going to talk about bus separation. Now, essentially, these are new inventions, new applications. When we first started with transmission system, I don't remember where the breaker failure. I don't remember, but maybe it's there. But what happened? Breaker failure is because we may have a condition. The main protection operate, but the breaker fail. Why the breaker fail? We'll talk about it. I'm also not 100% sure, okay, because they are so rare. So if the breaker fails, then what happens? The backup protection will operate. But the backup protection might be too slow. You can operate. So what is done is, we're going to put another level in between. We're going to have a relay that says, hey, for every circuit, we put a special relay called breaker failure relay. It's basically an overcurrent relay with some added inputs. So it detects that, hey, I've received a tripping signal. So what happened? I received a tripping signal. Within 100 milliseconds, the fault should disappear because of the breaker operation. What happened? The breaker fails to operate. Then I know something is wrong. What do I do? Well, I got two choices. We'll talk about that later. So that's breaker failure. Bus separation is relatively new. It's probably the newest protection scheme we have. And it's very different application from breaker failure. In the case of breaker failure, the relay operates, but the breaker didn't trip. And bus separation essentially is the relay failed to operate. So what happens? Now, so the breaker fails to operate, of course the relay fails to operate, the breaker cannot trip, so it cannot depend upon the breaker failure. So what do we do then? Well, we have a backup protection. What's the problem? The problem is, very often in a transmission system, we have multiple inputs. The simplest application, you have two parallel lines. So if the main protection fails, the next level of protection will be the backup protection of the lines. And the two lines will trip. So now you put in two lines. When one relay fails, you lose both lines. Obviously, that's no good. So what do? You then go and say, how does the current flow? One current will flow, the two current will flow through the two lines, and one of the current will flow through the bus section. So we're going to put a relay at the bus section. And if the relay detects, hey, I'm supposed to slip, the fault is supposed to disappear in exactly the same way as a breaker failure. Suppose it disappear after 100 milliseconds. And if it doesn't disappear after 100 milliseconds, something's wrong. I will trip the bus section and split the system. And that's why it's called bus separation. We split the system into a healthy section because you have a bus tie where there's no more fault, and with the other one there's still a fault, and that one will depend upon its backup protection to operate. So we save half the system. But that would mean what? The backup protection must now be slower because we have the main failure, main relay failure. Then we have the bus separation scheme coming in, and only then we have the backup. So the backup must be slower. So that's the price we pay. So in the case of a breaker failure, what do we trip? We trip a lot of breakers. We trip it as if it's exactly as if it's a bus bar fault because we don't know what happens. We trip the whole thing. So if you got in the case of an H arrangement, we got 5 circuits, 2 incomers, 2 outgoing feeders, one bus section. We imagine there's a fault on one side of the bus bar. We trip 3 breakers. So that's what we do with this breaker failure. Unless, of course, the bus section itself fails, then we trip all the 5 breakers. But with the bus separation, we only trip 1 breaker, and that is the bus section. So you can see the difference. Bus separation trips only 1 relay, the other will trip 3 to 5 relays for the same arrangement. Of course, we're going to talk about auto reclose of transmission lines. We also use it for distribution lines, but the application is slightly different. And then the last part, we'll then talk about testing of protection relays. Okay, so that's what we'll do today. So any questions before I start on what I have to say? Okay, any questions? Let me do something first. So I'll go through the revised notes with you. You should have received a copy. So the first thing I want to talk to you about is there is this thing called, I'll just go through selected slides. There's this thing called trips. If you look at this, you can see there are different ways of tripping. So at 275 kV for transmission lines and in the utility for transmission transformers, we have 2 main protection. If you have 2 main protection, how do you arrange them? So you can see this is a 2 out of 2. That means both relays must trip to get a tripping. And if one relay fails, we don't have a trip. And that's what we do with busbar protection. So the good thing is it cannot trip wrongly, but it can fail to trip. So then this is a weakness, and we have to see a way to overcome this weakness. Sorry, I'm getting mixed up. This is for transmission lines. My apologies. This is a transmission line. So we have 2 independent breakers. So with the one is called main 1, one is called main 2. So as long as one of them operates, you get a trip. So the second one is just an added insurance. If one fails, one CT fails, one relay fails, we still have a trip. So it's a 1 out of 2 arrangement. And you see you have 2 trip calls. Of course, then what's the problem? What happens if one relay trips wrongly? Then you have lost 1 line. And is there going to be a problem? In the TMB transmission system, there's not a problem. But in SEB system, we have seen problems. Why? Between Papan to say Bintulu, maybe the 2 lines, only 2 lines. So what happens? You take 1 line out for maintenance, and suddenly the other line trips. And now you have lost both links. You have lost completely Bintulu. Then we have a problem. So in a very well connected network like the TMB is a very well connected network. In general, this is not a problem. But for a system which have very few lines, this can be a problem. So that's a 1 out of 2. The opposite of it is a 2 out of 2. So that was the first one I call a logic OR, this is a logic AND. So both must trip. So we have a bus bar we have a discriminating relay, we have a check relay. So both relays must trip to operate a trip. So that means you cannot trip wrongly. Then what's the problem? If one relay fails, we have no protection. So this may not be acceptable. And at 275 kV, we have to find a way to overcome this weakness. At 132, essentially we don't. Okay, so how we do it? I don't have a drawing, but you can imagine this. We imagine that we have 4 CTs. So one CT goes to relay 1, one CT goes to relay the relay 5, relay 7. So we have 4 CTs with 4 relays, and we have a duplicate 2 out of 2. A duplicate 2 out of 2. So that means it's not likely to fail. One relay fails, we still have a very good protection. And that's what we do with 275 kV bus bar protection. But in SEB, Sarawak Energy, they do it slightly differently. This is the arrangement for SEB. Okay, so it's different from what you have seen here. So that brings me to a very interesting point, that whatever I tell you here, you cannot say, oh, I was told this is what happens, so this is what I'm going to do. You cannot say that, because number one, there have been an evolution. Since the day I was involved in protection until now, there's evolution. And the latest changes, I'm not even aware of some of them. So I had to call out some of you and say, hey, what was the latest way we do things? So what we do what we did long ago and what we do now are different. What we do in Sarawak, what we do in Semenanjung is different. What we do in TND, what we do in Dubai may be different. So we cannot take one application and say, yeah, this is what I'm going to design, I'm going to buy it, I'm going to design it. I don't have to wait for approval of drawing. You can get into trouble. So you have to accept the fact that not like distribution, is more or less standardized all over the world. Not 100%, but in general. But with transmission, there are so many variations. Okay, you cannot make a general remark. I give a very simple case now. I go back to this. We have 2 relays, we have 2 trip calls. In my days, as I remember it, because that was more than 30 years ago, relay 1 would operate trip call 1, relay 2 operate trip call 2. But this is no longer true of transmission practice nowadays. So what's the latest practice? Number one, you have to find out what's the standard be used by that utility. And only then you can find out. And maybe they are using an old standard, maybe they want a new way to do things. So before you do on a project, you better be aware that there are a lot of potential pitfalls. So that was the concept. The next thing I'll show you very quickly is this one asked by Kennedy. I won't go into detail, but basically there's a trip supervision scheme, and essentially what does it monitor? It monitors, number one, the DC supply is okay. Number two, it monitors that except for this PR, the protection relay contact, the rest of the circuit is in order. Now the fuse is okay, the trip hall is not open circuited. So what it does is there's a current, if everything is okay, there should be a current flowing through in this way. And then if there's a current flowing through this way, this contact will open and there should be no alarm. And what I said in the notes was that you can use the programmable logic within the relay to achieve the same thing instead of buying this dedicated relay. But what I've been warned is if you do that, there may be certain things that this scheme cannot do. I didn't go and look into it further. So take what I said with a pinch of salt. In other words, it may not be 100% true. I didn't look into it further. So essentially what this does, as I said, is that if everything is okay, a current will flow through either one of these or both of these coils. And if that's happened, that means everything is okay, and then this contact will open, we have no alarm. And if anything goes wrong, there will be an alarm. Okay, that's what it means. So Kennedy, I hope that answers your question. Okay, the next thing I want to talk about is I think will be the pilot wire and what we call the summation transformer. So as I told you, I left out pilot wire because number one, as I say, it's old technology. You may know what, we are probably people not interested. So I was wrong when I did a mini survey. There's so many things, there were so many people interested. Okay, so but I won't spend too much time talking about it because the notes are self-explanatory. So I will just go through the main points. Anybody interested, we can always come back. The question here is, I use the word protection elements. So this is a new notes. What are protection elements? Protection elements are essentially used for this. The word is actually used for distance relays. So what the protection element means is the measuring device, the one that actually causes the relay to operate. So let's look at overcurrent or fault relays. So if you have overcurrent or fault relay, in general, for overcurrent, we have 3 overcurrent. So if you want, you can say, we have 3 overcurrent protection, we have 3 overcurrent elements. But normally we just say 3 overcurrent protection. And then for a fault, we have 1. So that's what we have for overcurrent. Overcurrent or fault. But you find that at distance relay, we do it differently. At distance relay, for phase fault, we have 3 measuring units. And this is the time we really use the word elements. We have 3 phase fault elements for one zone. Then 3 for another zone, 3 for another zone. Okay, so we have 3 phase fault elements. What for a fault? In the case of overcurrent, we only use 1 earth fault relay. But traditionally, we have always used 3 earth fault relays, 3 earth fault elements for distance relays. So one zone, therefore, will have 6 measuring elements. 3 for overcurrent, 3 for earth fault. So you can see there's a difference. Why didn't we use 1 earth fault element? It's just to carry forward from the good old days. I'm sure there's a way we can actually save it, but nobody probably wants to do it. So that's what I meant. So in general, we need a minimum of 2 overcurrent relays, 2 for phase fault and 1 for earth fault in general. So you can see that they're slightly different. Now, what happens if you have a pilot wire? If you have a pilot wire, you must communicate between the 2 ends. So if you are going to have 3 overcurrent and 1 earth fault, or even 3 overcurrent, that means I need 3 communication channels. I need 3 pairs of pilot wire. I don't want to have so much. I only want 1. So how do I create a relay that is able to measure all type of fault, but by using only 1 element? That is essentially what we are, why we're using this summation transformer. So in the current differential relay, I forgot. In the current differential relay, we actually only use 3 elements. The 3 elements I use are both overcurrent and earth fault. So you can see there are 3 different ways of doing protection. And now we have the 4th one. So the 4th one is the pilot wire. We have only 1 operating coil. 1 pair of pilot wire, 1 operating coil. So how do you get information? How do you trip for different type of faults? So we're going to use this very special transformer. I'm going to call this transformer a 3-in-1 transformer, because we're going to add up the 3 currents in such a way it can detect any type of fault. So that's called a summation transformer, to convert the 3 phase quantities into a single quantity, a single unbalanced quantity. And that one should be able to detect all the 7 types of faults. So what are 7 types of faults? We have 3 earth fault, we have 3 phase fault, and we have a 3 phase fault, balanced or unbalanced. So we must be able to detect all these faults. That's why we're going to use this summation transformer. So the original summation transformer is what you see, but for some reason it's no longer in use. This is actually an old railroad drawing, but this transformer is no longer in use even within railroad. So what is this transformer? So you can see, okay, I'll show you the actual drawing. Okay, I'll come back to that. You can see these 3 CTs. You can see they're connected to this transformer. With how many inputs? A phase input, B phase input, C phase input. This is a neutral. And we have one output, which is a current. And that output there goes to the measuring element. So that's the one I said, this is a single element relay, single coil. And this coil is able to detect all type of fault, whether it's phase fault or fault, 3 phase fault. So in the original design, what we did was, we have an output, we have input current, we have output current, and we have this CT with different number of turns. So we imagine the secondary, it's not stated here, we imagine the secondary is only 1 turn, imagine. And we imagine that, hey, this one, R goes through one turn, B goes through one turn, and C goes through n turns. So what's the output of this? So the output of this would be IA multiplied by n plus 2, because R, the A phase relay, goes through n plus 2. The B phase will go through IB multiplied by n plus 1. And the C phase goes through n turns. And because they are added up unequally, this is able to detect three-phase fault using this concept. So you can see here again, Rn, n plus 2, Yn, n plus 1, Bn, n. What about face-to-face? Ry, 1. Yb, 1. Br, 2. How come? So that means what? Since the output of this depends upon the input current and the number of turns, that means that the one that is the most sensitive is the A phase fault, because A phase goes through n plus turn. This is a CT. So the more turns you have here, the more output. So A will have the most sensitive, and B less sensitive, C less sensitive. So the 3-earth fault will have different sensitivities. And similarly, the two of the earth faults have the same sensitivity, but one of them has got double the sensitivity. And if you can look at this logic, right, if you want, you can draw it out. You find that the output of this is √3. So if you have that, then if anybody really interested, you have to do a bit of reverse engineering. Why? Because if you can read the manuals, the old manual I talked about for 30, 40 years ago, you won't even find this. The new manuals, forget it, you will never find it. So I'm going to complicate things by making it a little bit more difficult. Why? I'm going to introduce that there's an n plus n, because I want to be able to show you how to calculate the sensitivity of this. Right? So we are saying that instead of the A phase going through 2 plus n, I'm going to say it's 2m plus n. So what's the sensitivity? The more turns, that means we need less current to operate. So the current required to operate is therefore 1 divided by 2 plus n. So you can see all the phases have different sensitivities, including the 3-phase fault. Okay? So now let us now go and imagine, can I simplify it? Okay, we're going to simplify by saying, let's imagine that m is 1 and n is 2. N is 3, sorry. So 1 divided by 2 plus 3 is 1/5. 1/5. That means the current sensitivity of the A phase is 20%. Nice number. What about for the B phase? It's 1 divided by 4. 1 plus 3, 4 is 25%. C is 33%. So you can see there are 3 phases of different sensitivities. And similarly, the face-to-face, one of them is double the sensitivity of the other one. And then we have one for earth fault and for 3-phase fault. So, but as I said, this CT no longer exists. So what really exists now is, you can see it's completely different. You can see, remember the figure I had was 20, 25, 33. The nearest is 33, 25, 32, and 42. And to do this, I have to introduce the M. And if anybody really interested, we can then do backwards. For example, the figures you see here, the figures that you see on the next slide, in red, 25, 125, and so on, these are taken from one particular relay that I've chosen. You see here? What did I put here? I put SOCO RF and 1 turn. Yeah, I've chosen this. 18, 21, 25. I think I've chosen a different one, sorry. Okay, I've chosen the C phase first, sorry. I choose C phase is 25 and AB is 125. Why did I choose those two phases? I can see the, sorry, I went wrong page. This is a C phase. So C phase is 25, AB is 125. Why did I choose that? Because the method, it makes it very easy for me to do the calculation. Why? Look at the equation again. C, if I know this is 25, can I calculate N? If I know AB is 125, can I calculate M?
Of course.
Isn't it? I calculate N and M if I know these figures. And I know the figures from here. C phase is 25, AB is 125. From there, I can calculate what is N, what is M. And once I know the rest, I know this, I can calculate what is the A phase sensitivity, the B phase sensitivity, the 3-phase fault sensitivity, and you can see the numbers I'm getting are very close to the actual answers. In fact, they are exactly the same. Like 17.9, 18, 20.8, 21, 32, 72. So I'm doing a bit of reverse engineering. At first, I couldn't figure it out. I told Win, I couldn't figure it out. Then I looked at it, yeah, the answer is so simple. That's what I'm trying to show you. So you won't find this anywhere in textbooks, anywhere in the railroad or so-called R manual. So they're doing a bit of reverse engineering to try to explain to you, in case you're very interested. So anybody got any questions regarding this reverse engineering? So now you understand why I chose to call it M and N instead of just 1 and N. So I need, because the equations that are used, M is no longer equal to 1, it's equal to some other value. Okay. Any questions? Last chance. If not, I just go through this last slide very, very quickly because it's very technical. How did we get that the 3-phase is equal to √3? How did we get that? So how you get that, you can see here. You can see this? There's a √3 here. And it also shows that the angle here is 30 degrees. So when you add up these three quantities, using these unequal values, the resultant phasor has a magnitude of √3 and an angle of minus 30 degrees. If I could ask you to do this, he says susah lah. You know what? There's a trick. You can do it very simply by ignoring one component. If you are really interested, what do we ignore? Now you can see here, the formula is 2m plus n, IA, and so on. But we know that when you add NIA, NIB, NIC, they're equal to 0. Isn't it? You add IA, IB, IC, 0. The 3 phases are equal and 120 degrees apart. So what can we do? We simplify the formula to 2m IA plus m IB. And then you put in these quantities. You can see here, my quantities here. This is 2, this is 1. Why? Because 1 is 2m, 1 is n. And if you do this simple trigonometry, this is square, the resultant quantity is a minus 30 degrees. And what's the magnitude? This is a right angle triangle. Square root of 2 squared minus 1 squared, square root of 3, which is exactly what we had earlier. So I won't go into this. Anybody interested, we can talk about it later. So any questions on this summation transformer? Incidentally, there are two types of pilot wire relay. For 33 kV, TMB uses the so-called RF. For 11 kV, TMB uses a translay. And I'm told that the translay is now hardly in use. So there are two very different relays. Okay. So any questions? Okay, we're going to talk about the distance relay. Okay, in fact, I don't think of anything to add to the distance relay. So you know that distance relays have different characteristics. We have a mode characteristic, offset mode characteristic, and then we have this quad characteristics. And I talked to you about the under reaching zone 1, over reaching zone 2. Okay. So anybody got any questions? Oh yeah, at the end of it, today we're going to do repeat the first test and then continue to do more tests. That's the last session for the day. I think we'll skip skip all these notes. If you got a question, you can stop me anytime. And then of course this the directional distance relay, busbar protection. So we spend a lot of time talking about busbar protection. So I just stop a little while here to explain about the diagram that I sent to you. I sent to you an AC wiring diagram for the busbar protection for a double busbar. And you look at it, you may get very confused, but it is actually based upon this. If you understand this, you understand that. And that is for a double busbar, you need to do switching. When the CD can be used either for the main bus or the reserve bus, so you must select by using this auxiliary contacts, which normally I call 52A, auxiliary contacts, normally open contacts. So when I say auxiliary, means that these are the main contacts of the disconnectors. These are the auxiliary contacts. So you can see if A is closed, then B is open, then the current comes here, then it goes to A, to the, in this case, the reserve busbar protection. Okay. So, and of course, there is also the same wiring diagram for tripping, because if the main busbar protection operates and this is on reserve bus, we don't want to trip it. So there'll be the tripping circuit also goes to go to A and B. I couldn't find a drawing for you, but essentially that's what it means. Okay, we are now ready to talk about the next section. I also sent to you a single line diagram. That's a suggestion of Johnny Ling. Johnny Ling, my old friend from Oman, actually from Sarawak Shell, and then he went to Oman. So that's where I spent a lot of time with him. And he suggested I send you the drawing. So if any of you got drawings or you look at any of the drawing, you can get a more practical feel. But as I said, don't use that and say, oh, I'm going to design my protection based 100% upon that. I don't have to talk to TNB. I don't have to talk to anybody. That's only a guide only. Talk about main and backup protection in transmission system. As I told you, what we do in distribution, what we do in transmission, number one, are completely different. And number two, what we do for one transmission project may be very different from what we do for another project. Okay, so be very careful. Whatever I say is only a general thing. You got to verify for yourself. Okay, so let's look at bus bars. So bus bars, if you have a single bus, typically a 132, then you need only one protection. Okay, in general, even a double bus, you also need one protection. Bus bars for 132, we give the simplest bus bar protection. But in the case of 275 kV, that's what I call EHB. Anything above 275 kV onwards, we have a duplicate bus bar protection. So we have two different bus bar protections. So, and each one of them has its own 2 out of 2 arrangement. So altogether, you end up with essentially 4 sets of CTs and 2 sets of protection. And each set of protection will have its own discriminating and check zone. So it can be very complicated and very expensive, of course. What's the backup protection for bus bars? It is the bus bar is the only equipment that I know that doesn't have any backup protection. Because you cannot go and say, I'll put another backup. You can put a duplicate, but we don't call it backup. And in general, as I said, we do overcurrent relay. So what we do, we then have to depend upon the distance relay at the remote end to give us the backup protection for bus bar fault at the end of the line. And for that, we use zone 2. Okay. Then lines. Lines is easy. We have current differential, and then of course we have distance relay. Actually, I forgot to put in here directional fault relays. So we have distance. The distance will give good backup protection for internal line fault, but for external faults, it doesn't work very well because the distance relay is set to cover only 120% of the first line. So if you got a line of equal length, then it can only cover 20% of the next line. So not very good, but that's what we have. Transformers, of course, we have all the main protection. We have the bias differential, we have restricted fault. Usually we have both HV and LV. How come I missed out the LV? There should be LV. Okay, and then usually on HV side, we also have an instantaneous protection. And then of course, the distance can also give some protection, backup protection. But in general, we depend upon your HV overcurrent or fault relays. Okay. And the other thing about the distance relay, it must not operate, it should not operate, especially zone 2, should not operate for a bus bar fault at LV. So in other words, it shouldn't go 100, zone 2 should not go beyond 100%. Otherwise, there may be a fault, and before the overcurrent relay can operate, your line relay trips on zone 2. So you got to be very careful. So that's one of the checks that you have to check. By the way, if any of you are interested in learning how to set distance relay, please look at the manuals. Some of the manuals. In fact, I wanted to do it, but wow, I have so much notes in the end. I stopped that. There are some examples of how to set some simple applications of distance relays. So let's look at internal fault.
Mr. Lee Kennedy here.
Yeah, Kennedy.
Just morning. Just now you mentioned about the bus separation also, and also about the backup. We need to give time for the bus separation to operate first before the backup operates. So normally for distance, is that the reason why they defeat the zone 1?
No, okay.
No.
Okay. Are you talking about one specific type of fault, or maybe
bus bar normally if
bus bar, okay.
Failure, yeah.
No, okay, let's start again. Okay, let's go back to the bus bar is protected by zone 2.
Okay.
So you can see that we have a zone 1, we have a zone 2, there's a zone 1, there's a zone 2. They are both essentially the same. So what happens is that zone 1, we forget about current difference. In the good old days, zone 1 is the main protection. So it's instantaneous, but it covers 80%. So you can never operate for external fault. So we're very happy with that. Zone 2 covers 120%. So what does it cover? It covers the rest of the 20% of the line. It covers the bus bar protection. It covers the first part of the next line. We okay?
Yes.
Now, why don't you set it instantaneous? We cannot set it instantaneous for a simple reason. Because we have other protections. We have a main protection for the bus bar. We have a main protection for this line. So if we will put zone 2 as instantaneous, for the bus bar fault, the bus bar protection trip, all the lines will also trip, which is not what you want, because the lines could be feeding it through a bus section. Are you with me?
Yes.
So we don't want zone 2 to operate for any fault outside this line. So for a bus bar fault, we say, let the bus bar be faster. My zone 2 must be slower. For a line fault, there's another line 1 here. So this zone 2 must be slower than this line 1. So it must be slower than these two main protection. Ideally, you want it to be as fast as possible for this area. But we cannot have two things. We cannot say, hey, I want it to be fast here, I want it to be slow there. It's the same protection. So only thing we can say, okay, in this area, the last 20%, I have no choice. Because of the need to coordinate with this, zone 2 must be slower than zone 1.
Okay.
Have I answered your question?
Yeah, okay.
Zone 2 must be slower than zone 1 because of the need for what we call coordination. But as you said, nowadays we have a current diff. What happened to zone 1? Can we leave zone 1 alone? That's where it comes to preference engineering. So number, can we have 3 main protection for faults in the first part of the line? Can we have 2 current diff and can we have zone 1 instantaneous? We can, but for whatever reason, TNB says no, SCB says no. If I got current diff, I'm so confident in my current diff, I don't want the zone 1, so they went and disabled zone 1. So when will zone 1 come in? Zone 1 will only come in if the current diff fails. I'm not too sure of the programming, whether that, what happens if one current diff fails, whether, because remember the 2 current diff at 275 kV, whether if one current diff fails, it activates the zone 1, or you need both to fail to activate zone 1. That one I'm not very sure. Maybe Fred, maybe you can, and the ETD guys, because you got three or four guys from ETD, maybe you want to answer this question, whether the programming is such that one current diff, one comms fail, one current diff fail, we activate zone 1. Anyone of you want to comment? Or you can comment a bit later if you want to.
Oh, normally I've heard this communication fail, it will activate, right?
Yeah, but now you got 2 relays. So when you say communication fail, what happens if communication fail for one relay? Will it activate as well, or you need the failure of both relays to activate it? That's why I'm talking about the detail. I'm not very sure. Okay, because all this came about long after I left LLN. Okay, so Fred, you want to answer the question? Fred probably not in. Okay, so Kennedy, have I answered your question?
Yes, thank you.
Okay, question. So in other words, in a way, you can say there's a lot of, well, we can do it one way, we can do it the other way. Which one better? Up to you lah. So in that sense, it's a preference engineering lah. Okay, both answers are right. Which answer you like, you choose the answer. In my case, I would say, since it's there and it doesn't do any harm, because distance relays, as far as I know, doesn't give you any problems, you might as well leave it on. Why not? You want free, but TNB and SCB decided not to have it. Okay, that's fine. As long as you don't have any adverse experience. If maybe one day you find, oh, there's an adverse experience, which has happened before. There was a case in Sabah where the current did fail, and I don't know, there was actually a high resistance fault. I don't know what happened to the directional fault. It didn't come in, and in the end, the whole system collapsed. Right? Don't know why the distance they didn't come in because of the high resistance fault. So any other questions? Some still outside. Here. So now we're looking at it from what are the type of backup protections we have. So for internal fault, local, when you have backup, the backup can be local, it can be in a remote substation. So in the case of a bus bar, there is no local backup. In the case of a current diff, yes, we have a distance relay as a backup. And of course, for transformers, the HV current for relay is a backup. What about local external? Now it's local, but it's not in the, for example, the line has a distance, the overcurrent relay has a fails. Then what's the backup? And usually we then depend upon zone distance. So it can be the distance for the bus bar. Bus bar, you can have bus bar at the back, you can bus bar in the forward direction. The bus bar in the forward direction will depend upon zone 2. The bus bar at the back will depend upon zone 3. But the zone 3, as I said, is so slow. The zone 2 at the other end will be faster. Okay. And then of course we have remote external. Remote external means the bus bar fails, protection fails. The next relay to operate will be the remote distance protection. And that's why the local, there is no backup specify the distance. It's only the remote distance zone 2, okay, because of the 120%, okay. And then of course we're going to talk about breaker failure and bus separation. So the backup relay operation can be classified as follows: operation following failure of the main protection, operation following failure of the circuit breaker. So we have two types of failures. Either the relay fail, relay meaning whatever is associated, maybe the CT, maybe the settings, and of course the other one is the relay operate, but the breaker failed to trip. So in the case of the first event, the usual practice is to rely on the backup protection as shown previously. So if the relay fails, we have another backup. We have a backup somewhere, okay? In the case of second failure, which is a circuit breaker failure, we're then going to activate a breaker failure relay, okay? And that will mean what? That will mean that we don't want the backup to operate first. That means the backup now must be slower than if you don't have a breaker failure. So that's the price we pay. So now distance relay looks very good, right? They are used extensively as backup. But please remember, distance relays are limited. Not because of the relay, but because of the settings. The zone 2 only protects 120% of the line. So it cannot go I cannot go 120% of the first line. That 120% can protect protect more than 100% of the next line. So you cannot protect the next line 100%. So there are limitations. Why? Zone 2 is limited. Zone 3 actually can protect beyond the line, but zone 3 is so slow. As I keep saying, if it ever operates, the system will have collapsed. So here you can see we have a distance relay. So what happens in zone 2? Now zone 2 is covering into the next line. Zone 2 will go into the transformer, and zone 2 will go into the parallel line. So in other words, you've got a fault on one line. These two lines are in parallel. This one will contribute a fault into this line here. And if the fault is within 20%, this can act as a backup. But if the fault is here, they may be in the middle, and if this protection fail or this breaker fail, this one cannot be a backup. It's too slow. So you got to be careful that distance relays are all fantastic, but they have limitation. And that's what I'm trying to say here. Zone 2A will overreach into the next line, as well as the parallel line. It does not provide backup protection for the whole of the next line. So please remember that. Here there's a slight mistake in the drawing. Essentially, to repeat, I made a mistake here. I just look at it last night. I saw it. So this one shouldn't go so far. I'll try to send you another set of revised notes later. It should go until here. It should not cover the zone 2. The other zone 1 is here. Zone 2 will cover the bus bar. It will cover part of the next line, the next transformer. So the next line is here, the next transformer, and it will cover part of the parallel line. But my mistake was that somehow I went and put it. I did overdid here. So then we're going to talk about bus separation. So bus separation is that when you're parallel circuits, is it good or not? Your parallel circuits? It's good. Why? Better reliability. One line trips, you still have the other line. But what happens if you have a fault and the main protection fails? So your transformer fault, transformer protection fails. Transformer, what happens? Now you have two lines feeding into the fault. And if you have nothing in between, the next bus bar protection and the next distance relay operation will trip both lines, and you have lost two lines. You got 4 lines, you trip all the 4 lines, which is no good. So therefore, what you can then do is to have what's called a bus separation scheme for parallel incomers. Okay, that's what we'll do, and we'll split the system. Okay, so the what happened is the fault is not clear. There's a fault. The fault is not clear. Why? Due to the failure of the main protection. It can also be due to the failure of the breaker, but that one initiates another sequence of events. Here in this case, talk about failure of the relay. So the main relay, and both may operate at the same time, by the way. So the main protection fails. Then what happened? The backup protection, the bus separation scheme will come in and trip the bus section. It only trips one breaker, the bus section, and then removes one of the fault contribution. That saves half the system, and then the other half can then, okay, no choice, I have to trip the incomer, I have to lose one section of the bus bar as if it's a bus bar fault. Okay, no choice. So it will then the backup protection will operate for one side. Okay, but again, this will mean that the backup protection must now be slower. You have to add one more timing stage because you don't want to operate it. You don't want to operate too quickly. So that's what we'll do. So this gives to give an overview of what we're going to do. Okay. So any questions before I continue?
Mr. Lee, can I read the last slide and the previous slide? The
Yep.
last.
Hold on.
Previous slide. Yeah, this one. So this.
You want me to read something to you?
Oh, okay, no problem. So this one require additional level of discrimination like breaker failure.
Yeah. Because both of them, I want to be faster than the backup. So we'll talk about that in a little while.
Okay. Thanks.
Thanks, Kennedy, right?
Yeah, Kennedy.
Yeah. Okay. So now we come to breaker failure. Now our breaker failure is very common. To be honest, in all my years, I don't remember any experience with breaker failures. Of course, what's the most common fault that I can think of is the trip cord open circuit. But we have two trip cords. Can two trip cord open circuit at the same time? Very unlikely, right? Are there mechanical problems? In my experience, I don't know. I've never experienced, but my old colleague Chua from Temco tells me that he thinks there are, but I don't have the details. I'm not aware of any case that I know of. Okay, sorry. There was one case, and that was, I don't know whether Kennedy, whether you're in NLDC. This is Tuanku Jaffa Power Station. There was a generator. I don't know the full story. All I know is there was a generator, they were running and they want to shut it down. My guess is that they sent a trip signal to trip the generator breaker 275 kV. What happened? The turbine, you know, when you trip a generator, you got to trip three things. You got to trip the turbine, you got to trip the field, and you got to trip the circuit breaker. And the way I understood it was the exciter, the field, and the turbine trip, but the breaker didn't trip. The 275 kV breaker didn't trip. So what happened? Now the generator is connected to the system, but with no mechanical input, it becomes a motor. So now you got this 120 megawatt generator that has become a motor. So you're trying to drive a generator as a motor. Of course, it's not designed for that. The protection can work, but there's no use because none of the breaker won't open. And apparently the story I heard was the shift charge engineer was trying to see, hey, how can we trip it and all that. Okay, the safest way or the only thing that you can do is to run into the switchyard, open up the circuit breaker, what we call local circuit breaker, what we call control, and use the manual trip. But probably nobody I thought of it. Nobody. I'm not going to run inside there with the breaker that fail. I'm not going to risk. So nobody wants to. Probably I don't know. I'm just guessing. And in the end, the only way you can switch off that was to isolate that, meaning that you transfer that all the loads. You isolate one bus so that you have only one incomer and only the generator that is running, and then trip off that. The bus section. No, you trip say one bus coupler or bus section. So you have only one bus section that is connected to that generator, and then finally trip it out. But you need time, and by the time they realize it, the generator was damaged. I imagine it cost millions to repair it. So that's the only incident that I know of. This happened probably about maybe 20-30 years ago. Are you aware of this, Kennedy?
No, I think before I joined.
Before you join, if you ask your old colleagues, Nohasby and so on, I'm sure they will be able to remember. Hey, Raslan, would you remember?
When Raslan joined.
Raslan before or after you?
After me. I think
you have to go back to your seniors. You must ask them to tell you all these horror stories. I got a lot of horror stories, but I don't have all the facts. Of course, the biggest horror story was the one in Parker, the one I'm sure Kennedy, you know, right? The one that caused the nationwide blackout, I think, in '92. And the other horror story was one in Port Klang, where when they did load transfer, somehow there was a mistake. There are a lot of horror stories. Maybe you're not allowed to tell them. Okay, so breaker failure is, we know that there's a protection relay operate, the breaker didn't trip. So what happens? So if the breaker didn't trip, then we need another relay that will detect it. And of course, you can depend upon the what we call the remote distance relays and so on. But in between, I may have one that may trip even faster, more definite. Okay, so we are going to have a breaker failure. So the occurrence of a fault in the transmission system should result in a clearance by a unit protection and its two associated breakers within 80 milliseconds. Usually I put 80 lah. Okay, so failure to do so is due to either the following: some form of protection relay equipment failure. We don't know what. It could be anything associated with the relay. And the other, of course, is a circuit breaker failure. One is a trip coil failure, which is the easiest one to blame. But trip coil failure nowadays not too bad because we have two trip coils. But if it's a mechanical problem, as I said, I don't know enough. I don't have any experience with it. Then of course we have a more serious problem. Okay, so both events will probably result in the operation of one or more backup protection relays. But the extent of the tripping can be minimized by the use of a breaker failure scheme. So there are two main variations of this 50BF. 50 is a NC number for instantaneous overcurrent, and BF, of course, is breaker failure. So we can have a single stage relay, okay, and then this single stage relay will trip everything connect as if it's a bus bar fault. So if you trip all the breakers connected to the same bus bar as this fail, we call it a back trip. So you got two incomers, two outgoing feeders, one bus section. So, and one of the relay fail, we trip everything associated with that one side of the bus bar. So as if it's a bus bar fault, we call it a back trip. The other one is to have a two-stage. So the two-stage would mean what? Stage one will try to trip the breaker again, re-trip. So a re-trip, and if that fails, we have a back trip. So that's what it means. So the concept of this two trip is as follows lah. So we have, as I said, after a short time delay, we send a second trip to the same circuit breaker. And then if that still doesn't work, then we then do a back trip. And that's the concept, as far as I know, is used in most utilities lah. So let's look at this case. So we have, in this case, 3 lines, 4 lines lah, and one of them is a fault. So what should happen? Well, breaker 3 and breaker 4 should trip. Assuming that breaker 4 tripped, but breaker 3 didn't trip for some reason. So what happens? You then have all this feeding into the fault. So what do you want to do? You have no choice. You have to go in. Number one, try to re-trip the same breaker. Didn't work. Then you have no choice. You have to trip this 3 incomers. So you lose everything on this bus bar as if it's a bus bar fault. And the usual practice is when you do that, just to be very sure, you also send a signal to trip the remote breaker. So how many breakers would you have tripped? Essentially, with 8 breakers, we have tripped 7 breakers. That's what it means. So trip breaker 4, breaker 3 fail, trip 1, 2, 5, 6, 7, 8. 1, 5, and 7 are tripped by a what they call transfer trip or a inter trip. That's what breaker failure means. So any question? So it's a horrible thing, exactly like a bus bar fault. It's worse than the bus bar fault in the sense that now you also trip. A bus bar fault usually doesn't trip the remote breaker. Now you trip also the remote breaker as an added insurance. So the concept is very simple. The concept of breaker failure is we have a protection relay. So if there's a fault here, we send a signal to trip the breaker. The breaker trips, the relay will reset, the trip signal will disappear, and the current will disappear. What happens if the trip signal didn't reset? What happens if the current didn't disappear? Then this will activate actually every time there's a fault, the breaker failure is activated, but for a short time. Before it can finish its timing, the fault has disappeared. So the breaker failure resets. So every time there's a fault, then it will start, but not enough time for it to operate. We purposely set it. So now the fault persists. The trip signal is still there, the fault current is still there. So the breaker failure will say, hey, something is wrong. I waited for 100 milliseconds and the fault current is still there. So, okay, let's wait a little bit longer. I will wait a bit longer and the fault current goes beyond a certain time. Then you trip everything on this bus bar and you send a signal to trip the other side. So we call it inter-trip. That's all. Sometimes they call it transfer trip. That's all. So very, very simple concept. So essentially this is what it does. So you can see this is the breaker failure relay. So you can see it gets a signal. I get a CT current flowing through the main protection relay, PR against protection, and it can also go through this breaker failure overcurrent relay. So there's an overcurrent relay inside there. At the same time, when the relay trip, it sends a signal to trip the breaker, but it also will send a signal to this breaker failure. So this breaker failure is getting two signals, AC current plus a DC trip, and it will then be activated. But before the timer can finish, both of these will disappear. The fault is cleared, the fault current disappears, the trip signal disappears. Then nothing happens. But if this loop persists, then eventually this timer will time out, and that's where we start tripping. That's all there is. Now, what I've shown here is just only not the real thing. The real thing is much more complicated than that. And there are a lot of variations of this. I tried to get a variation. I said, oh, too many, and I gave up in the end. Never mind, as long as you understand the concept. So, and you can see what happens when it trips. It will then trip everything. You can see here, it will trip this breaker, this breaker, this breaker, everything. That's what it does. Okay. Because we don't know what's happening, so let's trip everything. And these are typical timings that you see. So you can see, so under normal condition, we have a fault. The protection relay will operate, and after the relay operates, the breaker will take some time to operate, and that will clear the fault. So in other words, the protection relay sends a signal, the fault current is still there. A little bit later, about 60 milliseconds later, then the fault current disappears. And in the meantime, what happened? In the meantime, the CBF, the breaker failure, restarted. And if this disappears, then this also disappears. But if this doesn't disappear, then it continues, and there will come a time in the end, you say, hey, my breaker failure, you can see here, under normal condition, the breaker failure would have disappeared would have reset very quickly. And if it didn't reset, then we allow for another margin, and in the end, you say, if something has gone wrong, let's trip everything. And if you want to, there is a more detailed example here. Okay, I won't go into the detailed example.
Mr. Lee, just now, the earlier slide. Yeah, this one. What is local 86? Yeah, this one. What is local 86 operating time?
Oh, 86. Okay, breaker. 86 is what you can call as a master trip.
Oh, master trip.
Where is it? Where do you see the? Here. Okay, it's a master trip relay. So master trip, you will trip everything. Master trip, every circuit has its own master trip. So that means if you got a transformer, you got a line, you got a bus tie, everyone has it's a tripping relay, 86.
Okay, the next is local BKS is breakers. Is it? Breakers
Come
clearing time. BKS, local BKS clearing time. What does BKS mean?
I would imagine actually what it meant BKR. I imagine, because these are my notes. I just copy them somewhere. I imagine, but I don't really. It's a look. So in other words, how long do you so you now have the CBF operated. So what happened? It will send a signal to the master trip, to all the master trips involved, and then the master trip will then ask the local breaker to open, which is here lah. So now we are repeating this here, and by the time the fault current would have disappeared lah. And at the same time, you would have sent another signal due to a slight delay to the remote circuit breaker.
Okay, thank you.
Okay, and if you are really interested, then you can go into the next slide. The next slide shows you, I won't go into it. You can see here there's a first one, there's a retrip. So there is, when all this happens and the breaker fail, okay, no reset of CBF. If the fault current is cleared, the breaker, the CBF will reset, nothing happens. But now it didn't reset. So you get the timing continues. And at some stage, the CBF will operate. So what happens? It then has two timers. So the first timer will be timer 1. So we try a retrip. Trip the same breaker again. Okay. And then if that doesn't work, then we continue to another timing. Okay, here, fail, trip circuit breaker, retrip. Continue. Then we have a second timer, and that second timer will do a back trip. But the back trip is a trip everything that's on the same bus bar. Exactly like a bus bar 4. Okay, so the timings, if you're interested, you just go through these timings are based upon that lah.
All right, thank you.
Because obviously I don't want to, I can get bogged down in all these numbers lah. So, okay, so let's consider what happens if the transformer 87T operate, but the breaker didn't trip. So let's go and look at this. So we have a fault in this transformer. So in this case, we have two lines coming in, our H arrangement, a bus section, two breakers going to the breakers, and two breakers on the LV side of the transformer, two breakers going to the transformer, and the transformer on the each here. So the internal fault, what would happen? First thing that happen would be the differential relay operates. When differential relay operates, what will happen? It will trip this breaker. And it should trip this breaker. But this breaker failed. So now we have a breaker failure. So what happened? Now we have two fault currents feeding into the fault. Earlier we were not interested where this current came from. But now you have to worry. I got fault current coming from here through the bus section. We got another current coming from here. So what must I trip? I don't want to trip the, remember there's a backup here. If I trip the backup, I will lose both incomers. So I don't want to do that. So what do I want to do? I want to trip as if it's a bus bar fault. So the breaker failure will come in, retrip this. Didn't clear the fault. No choice. Now I have to go to a back trip. And the back trip will trip this breaker, and this breaker, 2A and 2B. So now we have cleared this fault as if it's a bus bar fault. So that's called breaker failure.
Mr. Lee, maybe can explain together with if there's a bus bar separation?
We will do that.
Okay, later.
We will do it because I can do it.
In the graph earlier slide, the timing, right, that you showed, where the bus bar separation will start. Can you also later share with us?
The later notes will come back. We can, if you want, we can come back later on, but later, because I will do one thing at a time.
All right. Okay, thanks.
So you can see it's a very simple concept. Okay, and later on we'll talk about timing. At this stage, I don't want to talk about timing. We'll leave that to a later stage. So any questions on this? So if you want to, then you go through the notes lah.
Engineer Lee, allow me to
Win, is it?
Shortly take a 1 second, 2 seconds break. I need to stop the recording and restart.
Oh, you want to take a break right now? Okay, can you wait a little bit longer?
It's done. I just need to stop the recording and restart.
Okay. So we take a 5 minutes break. You're suggesting, right?
No, it's okay. I'm restarted. Yeah. Okay.
Oh,
thanks.
so you want me to, do you want me to repeat what I just said?
No need. No need.
need.
It's already restarted.
Okay. I will be taking a break anyway, very soon. So what happens? What happens in real life? The bus separation scheme will also come in. Then we'll look at the timings, which we'll do later on, Kennedy. We'll look at the timings. At this stage, I will not look at the timing. So any questions? So the notes here are basically to say the same thing. Okay. So that's breaker failure for transformer fault. So what breaker failures can we have? We obviously can have breaker failure, transformer fault. We can have a breaker failure here. We also can have a breaker failure here for the bus bar fault. Then that creates a problem. Okay, because by the way, what it means is that every relay will have its own CBF. So there's a CBF, there are 5 CBFs here. So if, for example, this one, the bus bar protection sends a signal to trip. So this will activate the CBF here, CBF here, CBF here. And if this one fails to trip, this CBF can time out, and this CBF, in this case, we trip 3 breakers. But when this CBF fails, it trips all the 5 breakers. Okay. So,
Engineer Lee, if the main relay fails, will the circuit breaker, the backup, breaker failure protection also activate?
yeah, no. No, can you repeat the question?
If the main protection fails, that means the current, let's say, for example, the current differential fails.
Okay.
There won't be any DC signal to the breaker failure, right?
Yes.
So will the breaker failure still work?
What do you think, Win? As the name tells you, breaker failure. Did the breaker fail?
So it's not. Okay.
Because the breaker never got a signal, so don't blame the breaker for not tripping. So the breaker didn't fail, so you cannot. Because the whole thing depends upon how the whole thing starts, depends upon this. That you have a relay that trip that sends a signal. Can you see this protection trip? Yeah. So in this case, you get a current, but you don't get this. So the breaker is not, it didn't fail because it never got a signal. So this relay will not pick up.
Okay, thanks.
Okay. So that's breaker failure for transformer. Okay. So 50 BF will work. Now answer Win's question again. Breaker 50 BF will work only if the breaker fails to open after getting a protection trip signal. It will not operate for the following condition: protection relay fail. CT's got errors, VT's got errors. It won't work. Okay. So the first backup protection for a transformer short circuit is HV IDMT over current relay. But normally IDMT over current relay is an inverse curve, and the inverse curve may be slower. So you may say, hey, what about the backup? We have my transformer as a backup, but because of the inverse curve, especially the fault on the LV side, the relay might be so slow. It probably be slower than what we call the breaker failure. Typically for LV fault, the HV side we expect to operate in about 1 second. Here we're talking about less than about 0.3, about 0.3, 0.15, 0.3 seconds. So the breaker failure actually is faster than the backup overcurrent fault relay on the HV side of the transformer. Actually, HV side of the transformer only got overcurrent, don't have earth fault, which I did mention somewhere, but I didn't spend a lot of time. And on top of that, it has another protection. So we assume all these protection are not able to, either they're not able to operate, or they didn't operate, or some other problem that the relay failed to operate. This is what happens to a bus bar fault now. So now we have a bus bar fault. So what happened? In this case, this trip, this didn't trip. What happened? It will try to retrieve this, didn't work. These two has retrieved. So if the breaker failure will then send a signal to trip this. So there's a inter-trip signal to trip this breaker. That's why we need this to trip, because we don't know which breaker has failed. Could be the incomer. So we need this. There's one more I didn't show you, and that is if this one fails. Okay. If this one fails, effectively you trip everything. Because we don't know what's going to happen. We trip everything. But I didn't talk about that case. So that is breaker failure. Any questions? No questions? Okay, let's take a 5 minutes break. Let's have some music. There is my Okay. Okay, I'm back. So any questions? So no question, and anything we've covered, including the summation transformer. Okay, not, then we'll continue. So the next thing we'll talk about is the bus separation scheme. Now, this bus separation scheme is relatively new, and I don't remember reading it anywhere else outside Malaysia. So maybe there is, or I'm not aware. And definitely it wasn't there when I left LLN in 1986. So what is this bus separation scheme? Let's go and look at it. But there are quite a lot of differences between this bus separation and the breaker failure. And I have some comments, so let's go and look at it. So now, let's consider the H arrangement. You'll be hearing this arrangement. You've been hearing the word H arrangement many times. So the typical H arrangement is used for a consumer substation with two incomers, parallel incomers, two transformers, and normally closed bus section. So this will apply to that sort of project. And what happens if, again, the main fail, and this time the breaker didn't fail, but the main protection fails. So if the main protection fails, then we have two currents. If you don't do anything, we have lose both incomers at the same time. Bus bar 4, let's say on one side, you lose two incomers because that's what happens. So the purpose of this scheme is to prevent the total loss by switching off one of the fault currents through the tripping of the bus section circuit breaker before any backup protection works. So it allows the main protection to work as usual, but we don't want the backup protection to work first, because if the backup protection works, means we lose both incomers. All right. So okay, I don't have a drawing here now. So so what happens is, if you can trip off one side without tripping the other side, then you split the bus section into two. So the one part is healthy, discontinue operation. The other side has a fault. Then let the backup protection work as usual. That's what it means, okay. So the scheme may involve two additional distance relays. So in the TMB scheme, I don't remember hearing this in the SEB scheme. Correct me if I'm wrong, but I don't remember. So in the TMB scheme, what they do is they put in distance relay as this breaker this bus separation, okay, and this is shown in the next slide. So, for example, in the typical TMB scheme, we have, for example, in this case, I hope you can see it, but essentially you have a double bus bar with a bus tie circuit breaker here and a bus section circuit breaker. So this got a bus section. So a lot of people make a mistake, call this a bus coupler. This is not a bus coupler, it's a bus section. The bus coupler, as the name tells you, it couples the two bus bars, it joins the two bus bars. So this is the bus coupler. So what happens? You got a fault on the, let's forget about this one first now. Let's say we have this case. You have a, let's say in this case, we have two transformers going out. We got a bus section. They complicated it by putting in the what are disconnectors. So let's say all these are closed, right? So now transformer is energized. All these three disconnectors and circuit breakers are closed, and this is energized. So what happens? You got a fault. So if you got a fault, as I said, you got two currents coming in, one from here, one from the other side. And if the main protection works, that's fine. But if the main protection fails, the next stage would normally be the backup, and the backup would trip both incomers. So what they then do is they go to this breaker and put a bus separation relay. And this bus separation relay will say, I see a fault current. Hey, the main protection should have tripped. It didn't trip. Again, timing. So then say, hey, before the breaker failure, when they sees the fault current beyond a certain time, it knows that something has gone wrong. Either there's a breaker failure or there is a what we call main protection failure. So what it does, it trips this. So it separates the two systems now, no longer in parallel. So one side will say, I still have a fault, the other side say, I got no fault. And we do the same thing with a double bus bar. So we have this bus coupler, and we have a protection. They'll say, hey, if I see a current going through here for too long a time, something is wrong. So the question is, how do you detect this? In the TMB concept at the moment, they use distance relays. So they have one distance relay here, one distance relay here, and effectively they have another distance relay. So for this arrangement, they need 3 distance relays. Okay, I question the need for distance relays because number one, why do you need a distance relay? Because distance relay means I need 2, one to look forward, one to look backward. What do you want? You're looking for a current. But then why don't you put an overcurrent relay? So in my projects, I put in overcurrent relays, and so far I've not got any comment from TMB to say no, you cannot do it. Well, it still works because you said, why do you need a distance? So complicated. Distance relay is so expensive, so complicated. Okay, with so many settings. Overcurrent relay, I can put one overcurrent relay here, one here, and that's it. Okay, so that's my concept. So basically now you know every bus tie circuit breaker. So this is called bus tie circuit breaker. We need to put in a bus separation. So one here, one here. So in this case, we have 2 bus ties. We need 2 bus separation relays. That's all. I just show it and I come back to this. So in this case, I will put in a bus separation. In the original one, you can see here there are 2 relays. This is the original TMB. So bus separation 1, bus separation 2. And we need distance relay according to TMB. So I have, in my projects, I've replaced it with 1 overcurrent relay. Much cheaper, much simpler. And I think it will work just as well. Okay. So any questions regarding this concept of bus separation?
So engineering, repeat where the fault is?
Regardless of where the fault is, exactly. As long as the fault is in the 275 kV system, this will work if the main protection fails. So let's look at this. This is your question, Green, right? So let's go back to this. There's a fault here. The main protection fails. Not the breaker, the main protection fails. So now we have 2 fault currents, one coming this way, one coming this way. Do we care where the fault is? Under normal condition, the main protection would have tripped this, and this fault current would have disappeared. No problem. But if the main protection didn't work, and if actually also if the breaker failure didn't, there's a breaker failure, actually in both cases, so we'll talk about that later. How do you distinguish it? So in this case, let's concentrate on relay failure. So there's a fault here. This one trips, but this one didn't. Both didn't trip. And both didn't trip, we have a problem because there is another current coming this way. That's another problem. We'll not talk about it. So this didn't trip. So this one continues to see a fault, this one continues to see the fault. And they don't know where the fault is. They don't know whether the fault is on the line, on this transformer, it's on the bus bar, on this line, or this one. We have no idea where the fault is. How do you know? There's no way. Because this one only says I see a fault. Where is it? I don't know. So what we then do is, hey, since we don't know, why don't we split the system? Why don't we open this breaker? If we open this breaker, we switch off one of the fault current, because in this case, this fault current will disappear. So what are we left? We are left with one fault current. Does this relay know where the fault current is? It doesn't know either. Or say, I see a fault current. Hey, should I trip? Finally, this relay must trip. To clear the fault, this backup protection must trip. So if the fault is on the line, this one failed. Okay, let's say the fault is on the transformer. If this one failed, we hope the distance relay is able to see the fault. the zone 2. Remember, zone 2 may not be able to see the fault. If the fault is here, zone 2 cannot see the fault because it's a high impedance. So then we depend upon the overcurrent relay. If the fault is here, maybe you can see it. So zone 2 clear the fault. The fault could be on the bus bar. The bus bar protection didn't work. So this will clear the fault. The fault could be in the line here. This relay failed. The fault is on the line, and yeah, this relay failed. So we clear this. So regardless of where the fault is, one will trip to split the system. The other one will trip to clear the fault current, regardless of the location, unless of course the fault is here lah. If the fault is here, then this cannot see, then the IDMT overcurrent will trip lah. So we are assuming the fault at 275. Finally, we need to trip one of these circuit breakers, either this or this. So, Kennedy, I'm sure you got a question for me.
Now clear. Just if you want me to ask, just now you mentioned that you use the overcurrent relay.
Yes.
To simplify it, maybe you can explain, because won't the overcurrent chances of overcurrent to maloperate?
The overcurrent is simpler relay, very unlikely you maloperate. Distant relay are more likely to maloperate.
Oh, maybe you can share with us your experience, why they maloperate compared to overcurrent?
If you go back to a distant relay, number one, you need VTs and CTs. What happened, for example, the MCB trips? You got no voltage. And if no voltage, then what happened is no voltage. Actually, you will say that that means the fault is at the relay, but it doesn't. There's something called a VT supervision relay, and that will then block the relay from tripping. It blocks it. If you have a distance relay, remember you got this power swing. If you put it too small, maybe it doesn't work. If you put it too big, maybe it might trip on power swing. So you got, and then you have a lot. And the setting, how do you set this relay? Because coming from distant relay set impedance, you got long lines, you got short lines. So do you set it to protect a short line, or do you use it to set it to protect a long line? And you got all sorts of problems. Overcurrent relay, I need only one. No need to set direct. And the relays can be set in the wrong direction. But overcurrent relay, only one. The moment I see a high fault current, more than the full load current, something wrong, I will start. What can go wrong with the overcurrent relay?
Okay.
Mr. Lee.
Yeah, who is that, please?
Mr. Lee, Hyang is here. Good morning, Mr. Lee. Yes.
Hyang.
Yeah.
Didn't sound like you, Hyang.
Yes. Okay. Yes, correct. Can I ask a question on operation for the H system? I talk about double bus bar system. Can I ask a question on operation for double bus bar system? It's almost similar like yours.
Yeah, you can.
So let's say because now in a lot of TMB they're using double bus bar system.
You're talking about 275 kV, yeah?
Either 275 kV or 132 kV.
Okay.
So they have double bus bar system.
Yes.
They have main bus bar, they have reverse bus bar, reserve bus bar. Okay.
Yes.
Main bus bar they separate into two. One is a main one, that another main two.
Yes.
Then they use the bus section to couple it.
Yes.
Right?
Yeah.
Then between the main bus bar and reserve bus bar, they use the is it sorry? I make a correction. Between main bus bar 1 and main bus bar 2, they use the bus section to couple it.
Yes.
Whereas main bus bar and the super bus, they use the bus coupler.
Yes.
To define it, right?
Yeah, exactly correct.
So in operation wise, for example, I have two incomer from, let's say, transmission line or incomer from TMB. We have two 132 kV transformer outgoing.
Yeah.
Okay. Then let's say in this bus bar, let's say it's 132 kV bus bar. So how should the operation for the bus section and also the bus coupler? Should it be on or should be off? How the integrations
That's your question, is it?
Yes. Because that you can play around with either you on the bus section or you off the bus section, or you on the bus coupler or you off the bus coupler. How the TMB practice, and how should the pro and con for each configurations?
You are talking about private consumer or TMB?
Okay, and let's say we talk about from private side, then later we go for TMB side, or maybe we can talk about TMB side or later to commercial side.
Okay. If you ask me, the answer is very simple. It depends upon you as the operator. That's the answer. Because I don't know what you want. I'll give a simple example. I have a project down south, and the owner says, I don't want to para my system. Is it good to para the system? Sure. It's good.
You talk about para system is to couple the main bus bar 1 and main bus bar 2, right?
Everything close lah.
That means you're going to use the main bus bar, whereas the reverse bus bar will totally dead. Only use
No. It can be, when I say para, it can be any combination.
You talking about para is you close the bus section as well as bus coupler, right? Both coupler, right? That means
we energize everything.
Okay.
We energize line 1, say maybe on main 1, line 2 on the reserve bus. Close the bus section, close the bus coupler, everything.
Okay, understand.
Is that what you want? Is that better? Yeah.
That's why I also don't know. Maybe you share your knowledge. I need to get your advice.
So is that good? It is good, but also bad lah. Because you, as I said, for example, you then have to go and look at all this bus separation. I say the bus separation because that means you got higher fault current. You need bus separation and so on.
Yes.
You could have a project that says, I want my two systems to be totally independent. I have all this, but let's take a H arrangement again. I have all this, but I want to operate with my bus section open. The only time I close in my bus section is when one of the transformers is taken out or one of the lines are taken out. I only need that. I don't want the para. So it's up to you. There's no correct answer. There's no wrong answer. It's up to you what you want to do.
Yeah, because I understand that if let's say everything on, then the fault current is very, very huge. So that's
not necessarily. If you got a transmission system, the impedance of the line is very small. So whether you parallel 2 lines or only one line, the fault current is about the same. But if you got 2 transformers, then it's different. 2 lines, the fault current is about the same one.
Okay. So Ms. Lee, you can continue.
So in other words, how you want to operate the system is all up to you. I don't know whether it's true or not. Maybe I think Kennedy can answer this question. Now, I'm told in the TMB, now TMB has got, I'm talking about 1327, say 33 or 11. Traditionally, they operate the 2 transformers in parallel. We have two incoming transformers with a bus section, we close everything. But for some reason, I'm told that is no longer true, maybe in Selangor only, maybe. What they do is they split the bus, they open the bus tie. And they only close the bus tie using an auto transfer system if one of the incomers fail. Why? I don't know the reason behind that, but I'm told.
Yes, because I agree with what Mr. Lee said, because I also been questioned by TNB, because one of the project is talking about the distribution for consumer. One of the consumer, they're using 132 kV.
Yeah.
The input from NLDC and also GSO to us is talking about why you don't couple the transformer. That means on the bus section. That means the bus coupler still off. Why you don't want to on the bus section? But because they say some transformers, some TMB, they couple the bus section.
Yeah.
Of course, I also heard about there are some they open it up.
Yeah.
So that's why I'm not sure what will be the practice in TMB in general and what will be the pro and con. I think there's a reason why they open it and why they close it.
Okay, as I told you, I'm out of touch with what people practice. I only hear stories. So the story I hear is traditionally we always close. Let's take a very simple case. H arrangement, 2 incomer, 1 bus section. I'm talking about at 11 kV, 33 kV. We're going to close it. Over the years, they've always closed it. But as I said, lately, I hear stories that we no longer close it. Why? The reason was not given. But what they did instead was to put in an auto transfer scheme. Under normal condition, open the bus section. If the transformer fails, if the transformer fails, will initiate auto transfer. Why? I don't know the reason behind TNB, but maybe the fault levels are too high and so on. So there could be a lot of reasons. Unless you know the reason behind it, I can only tell you that I hear that it has been implemented. At least within KL Selangor, it has been implemented. I don't know outside KL Selangor. Maybe there is, but I didn't go and look into the detail. So okay, the answer, Hang, to your question is, it all depends upon you as the operator. There are a lot of very big, what you call, distribution companies. The biggest that I know is actually in Pengerang. Pengerang, there is a Petronas unit that actually buys power from TNB at 275 kV and distribute them to various transformers. Do you know how many transformers are there at 275 kV? Kennedy, correct me if I'm wrong, but what I understand is that Pengerang...
Mr. Lee, Pengerang actually, they have their own generator now.
Yes.
Actually, they sell to TNB and also they supply their own.
So they never have a distribution license. They're a public licensee. And you know how many transformers they have? They have 28 275 33 kV transformer. 28 within the area. I don't know how big is Pengerang. Let's say it's 10 kilometers by 10 kilometers, 100 square kilometers. Let's say 28 275 to 33 kV transformers. So how you operate the transformer? It's up to Petronas as the operator to decide. You can say, I want to open the bus section, I want to close the bus section. It's up to you. There's no wrong answer. Because when you operate in parallel, what are the disadvantages? Or there are a lot of advantages, but there's also a lot of disadvantages, right? For example, simple thing like, hey, you switch off the line. Hey, don't forget that there's a parallel in feeder. You got a guy who very familiar that, hey, he better go and switch off the other breaker before he said the line is de-energizer. So it depends on your competency level. It depends upon, for example, the fault level is very high. Okay, when you have this 275 kV operating, 30 kV operating in parallel, for the 30 kV bus bar fault, the overcurrent relay takes longer time to trip. So there are things that you may want to say, for the interest of safety, for various reasons, I don't want to operate them in parallel. So it all depends upon you as the operator. That's the final answer I'm going to give you.
Okay, Mr. Lee, thank you. But there's another question that similar to this parallel. If let's say there's two transformer, 275 to 132 kV transformer, right? Both number. If let's say they parallel in 275 kV, is it advisable for 132 kV the bus bar also parallel?
Wait. Okay. Before you can parallel at 33 or 11 kV, you remember I showed you this. Okay, you are going through a point that I've told you before. When you want the parallel systems, you got to be very careful. Let me see where the note is. You remember I told you about this problem? Okay, now I can't remember where it is.
Yeah, because the next question I will ask, would it hit us?
I want, since you brought it up, I think it's a bit before this. Many notes. Okay, let me see. Since you brought it up, I want to re-emphasize the point. You remember this drawing?
Yes.
Okay, what I'm trying to tell you here is, if you have got this arrangement, you cannot say, I go and close this bus section without closing this. Why? Because this is part of this A, by closing A, TNB allows power transfer from this substation to this substation. I hope you can see my cursor. Okay. Can you see that I'm sending power from the top line to the bottom line? You can see here?
Yeah.
P1 with 40. And there's a P2, a P3 with minus 20. So what it means, I got 40, line 1 is taking in 40 megawatt, and I'm sending line 2 at 20 megawatt. My bus section is closed. And if I close in this, because this is a higher impedance, basically the power will go through here, for here. for this 40 and minus 20. What happens now if I go and close in bus section here? And I go and open this. Yeah, tell me what will happen.
That's my similar question to you, but maybe it's a little bit different because the cable near the P4 and P6 actually replaced by the distribution transformer.
It doesn't matter. Okay, yes, let's take a simpler case first. Don't talk about the more difficult case. Take a simpler case. I open A, but I close B. This part of the incomers are the TMB distribution system. My loads are here. So what will happen to the power flowing here?
You mean P1 or P3?
No, the loads are there. Okay, these are fixed. The loads are fixed. These two are fixed. I need the 40 megawatt coming in. I need to export 20 megawatt. So under normal condition, I have like 40 megawatt coming in, 20 goes this way, and 20 goes to the loads. Right? I got 10 going to the load, 10 going to the load. So I have 10 here, 10 here, 40 here. So 40 here, I got 30 coming here, 20 going this way, 10 going this way.
Okay.
Perfect.
Okay. So the answer for P5 will be
okay. Now hold on, Hyang. What your question was? Can I close in this without closing this? So
no. My question is if let's say A and B is closing.
A and B should be closed. Okay.
A and B is closing. Would it be safe because it might create a circulating current?
Why is there circulating current? Yeah, I know you're talking about transformer later, but never mind, let's look transformer out first. There is no circulating current because these two impedances are equal.
Yeah.
If these two impedances are equal, then of course there's no circulating current. We'll come to that later on again. So what happens? You now go and close in this without closing in this. What will happen is you are still trying to export 420 megawatt here. But this is closed, this is open. So what will happen? The 20 megawatt will go to here, 20 megawatt come here and go out this way. And what happens? Your energy meter here will see, hey, I got 40 megawatt coming in, 40 megawatt coming in and 20 megawatt going out. So your metering can get screwed up. If you want to make it more complicated, then you can say these are transformers. Will there be a problem if you have transformers? Not if you do it properly. Not if you make sure there's an on-load tap changer properly regulated and these two transformers are on the same tap. As the notes will tell you that if these two transformers are not on the same tap, then you have a problem called circulating current. Yes, that is true. And has this happened before? I know one case in, I know one case in KLCC where this happened. And now they've got a big problem because they cannot figure out what they have, why was there this circulating current and how to sort out the bill. So before you close in B, you must close in A. So what happened? There was one project, was it SunPower, Kennedy, where they were supposed to be closed, but somehow TMB went and opened this by mistake, inadvertently. And what happened? Suddenly, this guy got a big bill. And luckily, they have their own digital power meter. And their own digital power meter showed there was an import and there was an export, and therefore the bill was in error. So you got to be very, very careful when you have parallel incomers. It's not your fault because TMB agreed to close this, but somehow it tripped for whatever reason, manually or due to somebody forgot to close it back, whatever. So we have this problem, potentially. So if you are a private consumer, what I would tell you to do is, since you got these digital power meters and they all have all sorts of alarms, if you go and see a reverse power flow, you better give your operators an alarm. A reverse power flow, something has gone wrong. Please sort it out urgently.
Ali, why we put the meter at that location? Why don't we put at BM1 and BM2?
Very simple. If TMB allows you to put a BM1, BM2, what happens if one day you decide to extend the bus bar and put another transformer and you didn't tell TMB?
Okay.
Will TMB know or not? You're metering only these two loads. Now I put in a third and fourth load, but your meter is not there. Your meter is only on the old load. Whereas if I put an incomer, I don't care what you do. You will always meter it.
Okay.
Have I answered your question?
Okay, thank you, Ali. Okay.
Who is that, by the way?
Shamsul.
Ah, Shamsul. Okay. So, I mean, technically it can happen. I shut down my bus bar for maintenance. Actually, I go and extend the bus bar and put in a new load. And the TMB will never know. Okay. Any other questions? Hyang, have I answered your questions?
A little bit. One more. Sorry, guys. One more. Just
Sure.
you mentioned that consideration is to avoid circulating current. First thing, the transformer will be the same.
Sorry, can you repeat some of that? Sorry, can you repeat the whole thing? There's a lot of muffle.
Yeah, just okay. I repeat again. Sorry.
You speak slowly. Yes,
bus bar couple in 138 kV. Can you hear?
Wow, somehow
Hello.
The question is muffled. I cannot. Can you repeat?
Maybe Mr. Lee, I call you offline. I don't want to disturb the class.
Okay,
I call you offline after they
I'll try to
discuss.
find a break and then you can call me. Because somehow, I don't know. I can. It's some parts got muffled and I cannot tell what you are saying. Not clearly anyway. Okay. Gentlemen, for your questions, Yang, Shamsul, Kennedy, Wing, thank you all for your questions.
Ayat Lee, I want to ask Samsul about 21 for main bus bar zone 1. Can you show the diagram?
Sure. You're talking about the distance protection again, huh?
Yes, distance.
Hold on. Okay. Maybe I don't know which one you really need. Never mind. What's your question anyway?
I want to ask for the 21 main bus bar zone 1. We measure two current to input. So we have two function or only one function?
Wait, I missed some part. Is it 20? Can you repeat? Is it 21 bus protection? Sorry, I didn't.
21 main bus bar zone 1.
Wait. Oh, you're talking. Sorry. You are talking. Sorry, I lost. I didn't catch what you meant. You are talking about the bus separation because when you said 21, I thought of the line protection. Okay, sorry.
Bus separation.
The TMB scheme is they have two relays. I imagine one relay is looking in this direction, one relay is looking the other direction. So you have, okay, in other words, is there an arrow there? You can see here, there is one. Okay, this is for the reserve bus. So the reserve bus is at the bottom here. I can see the reserve bus. This is for the main bus 1 here. So and hold on, Samsul. And this one is for the main bus 2. So this one. Okay, he's saying that this is covering this. I wonder whether it's mixed up. Never mind. Okay, so one is covering this section of the bus, one is covering the other section of the bus, and one is covering the reserve bus. Okay, that's all we need to know. Okay, what was your question? So they are all looking forward into the bus.
Yes, just want to ask about the distance protection for main bus bar zone 1. They sum the current or they have two function. Either they have one function with they sum the current, or they have separate function in 31Z. F31Z.
Okay.
I want to know about
it. It is just a relay with the impedance setting. So the essentially, okay, let's take this one easier to talk about the reserve bus. If I have a reserve bus, I'm looking into here. So whether the fault is in the reserve bus or whether the fault is on the lines being fed by the reserve bus, we don't care. I'll give you a simple example. Let's say the line is 10 ohms. How TMB set it, I don't know because I've never done this. Let's say TMB either set to 80% of the line, 120%. So it's 10 ohms. To make it simple, let's say I set exactly 100%. So I will set to 10 ohms looking forward into this line. And then this one will maybe 10 ohms looking into this if the line goes there. So if you ask me to guess, I would say all three of them are set in the same way. They're looking forward into the bus bar.
Okay. For bus zone 2, we protect the main bus bar 2. So the direction of current is toward the bus bar 2. But for
it must be towards the protected bus bar.
Yeah.
Yes.
For the main bus bar zone 1, we have two current. One is current at Q12 and another one is at Q2. So yes. So we have two function, or we have one function for the main bus bar.
They're both the same function. All these have they are basically the same function.
Same function.
Okay, let's do it very simple. Let's take a case. They always simplify the problem. Hey, what happens if this is open? If this is open, this relay will take care of the one will take care of the left side, one will take care of the right side.
Okay.
Okay. Now we went. Now let's open this one instead, and let's close in this. So one will take care of the top, one will take care of the bottom. So they are looking into the bus bar.
So at one time we only close one breaker.
It's up to you.
Okay.
Because there's no restriction. Otherwise, hey, I put in this and now suddenly I cannot operate my system in the way that I used to do before. No, there's no restriction. As long as the fault current coming this way, this relay should may be able to pick up.
Okay.
So let's put it this way, if I got it should be able to work regardless of the flow. Is there something troubling you, Shamsul?
Maybe if you have the setting, maybe.
No, okay. Let's look at a simplified drawing. Okay, so you can see in this case, one relay will say if I were doing it, I would say I want this relay to look into here.
Yes.
Including the bus section. So I say this relay is set to look here. So how would I set it? It doesn't matter. For example, let's say the line is 10 ohms. I'm going to set it at 10 ohms exactly. Make a simple example. So I will set this at 10 ohms. So as long as the fault is somewhere within this line, maybe the fault current has been fed by this way. Okay, maybe for example there's a fault here and this relay operate, but this relay didn't operate. There's a fault current been fed by this way. So I want it to trip. So I set it at 10 ohms to take care of the biggest fault current, worst fault condition. Maybe 12 ohms. And similarly, this one is set to operate for faults in this way.
Okay.
So you can see also the complications of having distance relays. You need to know, hey, what is the impedance of the line? And the worst thing is what happens, I got a long line and a short line. I got 4 lines here. Some are long, some are only 10 ohms, some are 50 ohms. Then how do I set it? Do I set between more than 10 ohm, more than 50 ohm, or somewhere in between? So you can see you have all these questions that you have to answer. And as I said, I've never done for this project for TNB, so I don't know how TNB wants to use it. I don't know. I only can tell you that there is such a thing. Unless you actually what Venkat has done is he has given me some of the relays settings for some typical project, but I don't have the line settings, the line data, so I cannot relate them to anything that makes sense. So have I answered your question within the capability of my knowledge?
Okay, Ali. Okay, it's okay. Thank you, Ali. Okay.
But as I said, why you make life so difficult? Why don't you put in one overcurrent relay? And this overcurrent relay doesn't care about which direction. So, and it is so simple because I know the fault current. The fault current, for example, let's say it's 20 kA. My maximum load current is say 1.5 kA. I set at 2 kA lah. Pretty here. Why do I need to worry about all these funny things? Direction. What's the impedance and all that? I need 3 relays, which are so expensive. Which things can go wrong. I don't know how to set it. So that's my feeling. And there was a project that we have done previously where the original concept was approved without a bus separation. And then they came back later after the project has been constructed. They say, hey, you need a bus separation and we need a distance relay. So I told them, you know, I got overcurrent relay there. I'm going to use it. And the TNB people accepted it. So you don't have to go for a high-end solution, which is more complicated unnecessarily. Okay. So any other questions? I didn't know there were so many questions on this bus separation.
Mr. Lee.
Yeah.
Yeah, this is Agung.
Hey, Agung.
For the bus separation using overcurrent that you mentioned, is it including the earth fault relay?
Okay. Agung asked a very sensitive question in the sense that, in general, TNB doesn't allow earth fault relays in transmission systems. So at 275, 132, 500, there is no earth fault relay. So even the transformer, if you put a relay here, there's only 51, there's no 51N. I don't know whether you're looking for something more than that, Agung.
No, it's
now, of course, you can ask why no earth fault relay. That one is a Cerita line. Anybody who is interested in Cerita line, we can talk about it separately. Are you aware of that Cerita line, Agung?
Yes.
Yeah, okay. That's what I would have thought because with your experience. Okay.
Thank you.
So far, as I said, I've never seen earth fault relays. The only earth fault relays we have seen at 128 or a transmission system are number one, directional earth fault and restricted earth fault. Other than that, I've never seen any earth fault relays. And there was a project in Sabah. The guys went and activated the earth fault relay and somehow in the end caused their generators to trip. So the bus separation scheme will be of little interest if the bus section circuit breaker is normally open. So if, for example, you go and say, hey, under normal condition, this breaker is open because I don't want to parallel my system. Remember, I told you, it's up to you to define what you want to do. So I don't want to parallel my system for whatever reason. So in that case, if you don't want to parallel, then this is open. And if this is open, then this bus separation scheme is of very little use. The only time you probably will close it is if you take one transformer out for maintenance or one line out for maintenance. That's the only time.
Mr. Lee, on here.
Yep.
One question. If they use the distance, do they set the earth fault for the bus separation scheme?
The earth fault? Why suddenly got? Oh, you mean talking about the earth fault in the distance relays?
Yeah.
I would think so, but I don't really know. Have you ever done it?
That's one that I said that actually, they use the earth fault. That means the distance also. I guess that's why they ask for distance, because you can also set for the earth fault.
Okay, Ong of course very familiar with what do you call this setting. So let's go back to the good old days when we have overcurrent relays. We have overcurrent relay as a backup, and we never say, hey, there's no earth fault relay. Why? Why do we worry about it? We don't, because earth fault currents are so high. So we don't need to worry. So that will be the answer I give, that we don't need to worry about earth faults, because earth fault currents can be as high as overcurrents. And that's the reason why, one of the reasons why we don't need earth faults at 122 kV or at transmission levels. Maybe you want to share anything about how you did the setting for your distance relay for your project?
Okay, the distance was set at 120% of the line.
Of the incoming line?
Yeah.
But you only got one incoming line.
So zone 1 is off, zone 2 is 120%.
120%.
Yeah. Then zone 3 was, I think, the same, 220%.
Okay. So you are saying that it is set at the line. So if you got one line, it's very simple. But in the transmission system, if you got say 2 or 4 lines or more, then how do you say 120%? Which line now? The shortest line or the longest line? So then you have to worry about it. In Ong's case, because it's a consumer substation, very easy. But if the TNB substation, it may be a bit more complicated. Anything else you want to add on?
No, that's all.
So
Thanks.
now, so based upon the typical timing, so let's compare the two of them between breaker failure and bus separation. The 50 BF would, so this is based on typical settings that I have seen. But as I say, all these things can change, or maybe I'm out of date. So the 50 BF will trip the bus section circuit breaker. Okay, 50 BF, why is it through the bus section? In the 150 milliseconds. The BS, bus separation scheme, will trip it in about 300 milliseconds. Why is there separation? I don't know. There's a TMB setting. So in other words, let's go back to this. This is the question I think Kennedy was asking. If there are two events that can occur here. This one showed a relay failure. So what I'm saying that if there's a relay failure, according to what I know, based on TMB setting, this relay will trip in 300 milliseconds. That means what? The backup here must be slower than 300 milliseconds. So you could add 300 and maybe another 150. So the zone 2 here will end up with 450. Okay, so that's our based on this. The 21Z is typically set 300 milliseconds. So the line then would have to trip in 450. Okay. What happens if you now have a breaker failure in state? If you have a breaker failure in state, the breaker failure will trip all these three, guess what? In 150 milliseconds. 50 BF will trip. Actually, the bus section is wrong. It should be all the breakers. The breakers in 150 milliseconds. So what will happen? So in other words, we don't know what will happen. We don't know whether it's a breaker failure event or it is a bus, relay failure event. So if it is a breaker failure event, within 150 milliseconds, okay, we would have tripped all the three, and then, we have tripped all the three. And then, of course, if anything goes wrong, then this will then trip in. If, for example, this breaker failed, then we see it didn't trip, then this will trip in 450 milliseconds. So from 150, the next step is 150, the next step is 450. We have 300 millisecond discrimination. Whereas in the case of, let me see whether I get it correct or not. Yeah, it's correct. It is. The breaker failure will trip in 150, and the zone 2 will trip in 450. What happens if it is a bus separation? So the bus separation, when this relay fails, this will take 300 milliseconds to operate. So the question that in my mind is, why delay to 300 milliseconds? Because the two events, the breaker failure and the bus separation, are completely different. Why do you need to make the bus separation so much slower? Why don't you put it to 150 milliseconds? So I couldn't figure out in my mind why TMB chose such a long delay. Okay, because by putting this for 300 milliseconds, that's where I need to end up with 450 milliseconds here. Which means that if there's a bus bar fault, this will take 450 milliseconds to clear. Which, if you ask me, I think it's too long. If you ask me, in other words, I would have put the breaker failure at 150. I would have put the bus separation at 150. I cannot think of a reason why I need to grade between these two, in other words. So, Kennedy, does that answer your question? That eventually, of course, is there a worst case in the sense that, is there a worst case that there is a breaker failure, there is a failure of this relay to trip? If this result fails to trip, then in the end, the breaker failure will trip everything here.
So looking at that, Mr. Lee, when the bus separation will operate if there's no If there's no breaker failure event, so does that mean?
Okay, there's no breaker failure, but what is the event? Is it a relay failure?
What are other events that can cause the bus separation to operate?
Come again.
What are the events that can cause the bus separation to operate besides breaker failure?
The only one is the main protection, the current flowing this for too long. That's all. So this one is basically an overcurrent. In the way that I designed it, this is an overcurrent relay. If I go beyond 300 milliseconds, something is seriously wrong. I trip this. I don't know what the event is. I don't care. As long as I see a current flowing for more than 300 milliseconds, I trip. So in other words, the BS will trip the bus section. It's an overcurrent relay connected to the bus section. And as long as I see a current of more than 300 milliseconds, I trip.
Okay, all right.
So what the fault is, I don't care. Okay, whether it's a CT failure, whether it's a VT failure, whether it's a relay failure, I don't know. And obviously it's not a breaker failure because we already passed the time for the breaker failure. Or it can be a breaker failure actually, okay, but a breaker failure and somehow the bus section didn't trip. So in other words, okay, let's take the worst case. There's a bus bar fault. This one, all these trip except this. The breaker failed, right? So the breaker failure will come in, and it will try to trip itself. Didn't trip. It will try to trip this. No use because we already tripped this. So the breaker failure will continue to time out, but it's no effect. So what's the next stage? Next stage will be the what we call the bus separation. Also no use because bus separation is tripping this. So fault current is still on. What the last thing? This will then trip. You want me to repeat the whole thing? Kennedy?
Clear. It's clear, Mr. Lee.
Anybody needs me to repeat the whole thing? Is there a worse situation where both happens? Breaker failure and what we call relay. Actually, is a relay failure, about breaker failure. So in other words, there is a fault at the bus bar. So this three should trip. These two trip, but this one didn't trip. So breaker failure will come in, try to trip this, cannot trip. It will trip this, no use because it already cleared the fault here already. Then what will happen? The bus separation will come in and try to trip this again, also no use. So fault continue and finally this will have to trip. Sorry, I was wrong. Okay, sorry, I was wrong. I apologize, I was wrong. If the bus section, if this, okay. The breaker failure here, I was wrong, sorry, I missed one thing. The breaker failure here will actually trip 5 breakers. Sorry, I was wrong. If there's a breaker failure here, all right, this relay, I saw a break, my relay failed, I don't know what's the problem, I will trip all the 5 breakers. So before the bus, I correct myself. So before the bus separation scheme can come in, it would have tripped these 2 breakers. So the bus separation scheme doesn't come in at all. So the most dangerous place or the most difficult place for it is the breaker failure here for this operate. Then we don't know where the fault is. If the breaker failure for this operate, then you will trip these 3 breakers. But the breaker failure for this to operate, you will trip 5 breakers. So every circuit has its own breaker failure. But the bus separation only are connected to CTs at the bus section. So any questions?
Mr. Lee, Chiu here.
Hey.
Back to that, the breaker failure of this bus section. Does it only trip the upstream breaker only?
No, the breaker failure.
Yes, of the bus
I just told you that the breaker failure of this will trip all these 5 breakers. And whenever the breaker failure happens, it also will trip upstream. Breaker failure is the only one that trips the upstream breaker. Bus bar protection, bus separation doesn't trip the upstream breaker.
No, I mean the immediate upstream breaker only trip.
No, it will. Whenever the breaker failure operates, it will trip the upstream. For example, let me put it this way. If there's a breaker failure here, and you try to trip this, what happens? Fault is still there. So you have to trip the upstream.
Oh, the immediate 2 upstream breaker. I mean, I thought it's surrounding the bus bar incomer and the outgoing breaker. No,
as I repeat what I told you. If there is a breaker failure of any of these buses, anyone, it will re-trip all these 3 breakers, and finally it will send a trip signal to here. So in this case, it will trip actually 3 local breakers and 1 remote breaker. Breaker failure is the only one that does the remote intertripping. Bus separation doesn't do it. So have I made it clear? SK, have I made it clear?
Okay. Thanks.
So in other words, what happens if the fault is here? If the breaker failure is here, you will trip all these 5 breakers and you will trip these 2 breakers. So this will then end up with tripping 7 breakers. And then the NLDC people like Razlan will be trying to find out what happened. So many relays tripping, very confused. So you have to go to the substation with the most trippings, and that's where probably there's a problem there. So you have to understand how the scheme works.
So engineering, is there? I mean, I believe there will be a scenario where a breaker failure tries to open the bus section, but the bus
breaker
section
failure will always open the bus. Try to open the bus section always.
So the bus section fails to operate.
Yes.
Then the next breaker failure of the bus section will try to operate the remaining breakers.
Yes,
So,
I just told you that if a breaker failure here will trip in the end 7 breakers.
okay.
Because we don't know where the fault is. We don't know fault on this side or that side. And we don't know which relay has. And we know that this must have failed to open. Because there's a breaker failure here, there's a breaker failure here, there's a breaker failure here. So there are 5 breaker failure relays here. So when this one happens, we know that it is this relay that failed. And when this relay fails, we have to trip all the 5, plus the remote 2. So 7.
So when, I'm not sure whether it can differentiate whether it is a second time it is detecting breaker failure and is now acting faster.
Come again?
I mean, if a breaker fail X is already 150 milliseconds delay, so the second one would add additional delay. So it may have already allowed the other distance protection to...
No, you cannot because of the timing. Your breaker failure is 150 milliseconds. Your backup is 450 milliseconds.
Okay, so probably it still needs to be more than 300 milliseconds. The backup.
Yeah, the backup. If you ask me, my opinion, but obviously I didn't go and look into it further. By first impression, I would have put it at 150, and I would have put it at 300. So why TNB delayed it at 300? That's the part that puzzles me. Because this tripping is a very minor tripping, only trips 1 breaker. But this tripping is a more serious tripping. So if you say that this is a more serious tripping, then maybe you want to delay it. But it's only 1 breaker, and it's already been tripped by the breaker failure anyway. So why do you want to make it slower than the breaker failure, which is a more extensive tripping? So why don't you make it the same timing? In fact, it should be the other way. This should be faster and this should be slightly slower, if you ask me. So by putting in this, as I say, I'm doing reverse engineering because I don't know whether, have you got any settings that of a similar nature, Ong?
Sorry, what's the question?
Have you got any experience with settings that are similar to what I've shown. These settings that I've shown is based on what Venkat gave to me.
Yeah, the bus section, yes, it's 300 milliseconds.
300. So I got two different settings. That's it. And the breaker failure is how much is it?
Yeah, the second, the retrieve. Sorry, not the retrieve. The back trip is 150. Yeah.
So I've got two different settings that confirm that, and then the backup is 450. Is it? The distance.
Zone 2. Zone 2. Wait. Zone 2 cannot remember. Yeah, I think typically it's 250. Yeah.
So I'm just trying to do reverse engineering. As I said, I'm no longer active lah. I've done reverse engineering. I say, hey, doesn't make sense to me. I'm no longer in touch with TMB lah. So unless I can go and talk to TMB and say, hey, this one, and they may say, hey, this is none of your business in the first place. You are no longer doing settings, so they may not entertain me. And a lot of my friends are doing this settings. Only one of them is still around lah, but I don't want to catch out him lah. So whatever I say, by the way, please take it with a pinch of salt. Don't take it to be the, what you call, don't take what I say is 100% true, 100% valid. There could be other reasons which I have not thought of. I'm just trying to, as I say, do reverse engineering. And when you do reverse engineering, sometimes you don't understand what is the reason behind the concept. So I'm not doing reverse engineering based on the limited information. It doesn't make sense to me lah. So maybe there's a valid reason.
Sorry, Mr. Lee, just confirm, yeah, zone 2 is 450 milliseconds.
Yeah. So when you do all this, you see, you delay all this, like what Ong said. Now you got a bus bar fault, you take 450 milliseconds to clear the fault. 450 milliseconds. Remember the original concept was to clear the fault in 100 milliseconds. Now you have 450 milliseconds, which is way too long, if you ask me. We're talking about 275 kV bus bar fault. So okay, I didn't know that this topic is so interesting. Any other questions? So this essentially is a repeat of what I said earlier lah. So the main protection will trip in 20 milliseconds. The TMB settings is the retrip is 80 milliseconds, which is a little bit too fast. The back trip is 150. The bus separation is 300. The zone 2 is 450. And the zone 3 is 3 seconds. And that's where it makes it terribly, terribly slow. Okay. From 450, you jump to 3 seconds. As I said, to me, I don't think it sounds logical. I mean, but we have been using that for a long, long time. It goes back to history. Okay. So, okay, let's do a comparison between breaker failure and bus separation. So, system condition, breaker failure can be used for either independent or para. Whereas, hey, I keep seeing this error. I don't know why. How many times? Keep correcting it. Keep coming back. It's bus separation, not sus. How many times? It's meant for para system. If you don't have a para system, this has very limited use. Okay. So what's the purpose of breaker failure? To trip all possible sources of fault after a breaker has failed. Okay. And the bus section is to switch off the para fault incomer. So if you can switch off the bus tie, then you now only have one fault current. Okay. After the main protection failed. So initiating is the relay trip signal did not reset because the fault is still there and the current is still flowing. Those are the initial signal beyond the normal fault clearance time, which is assumed to be 100 milliseconds. And then this one is the continued flow of the fault current through the bus tie circuit breaker. So this must be through the bus tie circuit breaker beyond the fault clearance time. Main relay operation, yes, in the case of breaker failure, no, in the case of bus separation. And circuit breaker failure, yes, and the other one, no. Okay, it's a relay that failed. And the trip signal, so all circuit breakers connected to the same bus must trip. This one only trips the bus tie circuit breakers. Any questions? We continue. So what type of relay do we use? We use a okay, here maybe I should correct myself lah. Here I put definite time current operated relay. So for bus separation, actually I should have put down there distance relay also lah. Intertrip signal, breaker failure, yes, we intertrip. Bus separation, we don't intertrip. So the worst case is we trip all the circuit breakers to the fail bus bar. Okay, upon failure of the bus tie circuit breaker, and the bus separation, the worst case is they only trip the bus section, so there's no worst, only one case only. And type of number of relays. So in this case, we use overcurrent relays and 1 per circuit. Whereas for the bus tie, bus separation, we use distance or overcurrent relay and only at the bus ties. So we can have up to 3 distance relays, okay, or 2 overcurrent relays. So what's the basis of setting? So must be slower than the main, faster than the backup. Typical TMB time, so I've given to you this before, like this is a repeat. And what is a backup? The backup will be zone 2 of the remote distance relay. So any questions? So this is again parallel operation. So just to show you only to show that hey, there's a fault current here, there's a fault current here, and because of this fault, there's a fault current coming through here, and your bus separation is a trip of this to save half the system. Half the system got no fault, half the system still has a fault. Now you concentrate on clearing this fault. Okay, and as usual, I've only shown you for the H substation. So so you can see that in the case of a breaker bus separation, we only trip this breaker. Whereas in the case of a breaker failure, this one can trip one side, you can trip their side, or you can trip, and if the breaker failure is here, then we trip everything. Okay, that's what it means. So we have 5 breaker failure relays. Okay, and the breaker failure for the bus tie would trip all 5 circuit breakers. Whereas in the case of bus separation, only one, maybe 2 relays, 3 relays, and only trip the bus tie circuit breaker. So completely different. Okay, any questions? Oh, I'm running way behind time already. I thought I was ahead of time, now I'm behind time. Wow. Okay, I will do this very quickly. So you have to give me the answers. So hopefully all of you will take part. But later on, I will ask you this more or less the same questions in the test. But I'm running way behind time because it's 11. I need 1 hour left. I don't even know I've got enough time to do the test. Okay, what's the total number of circuit breaker failure relays? So we're talking about H arrangement. Top test is H arrangement with 5 circuit breakers. So how many circuit breaker failures do we have? 1, 3, or 5? Anybody want to give an answer? 5. Shamsul, you want to try? Sorry, does somebody give an answer? Who was that?
Munira, 5.
5, yes. Who? Oh, Munira.
Yes.
Munira is from
I'm from
Intel.
Yes.
Okay. Thank you, Munira. Very good to hear your voice. Okay, what's the total number of bus separation overcurrent relays? I'm not overcurrent for this H arrangement. So how many do we have? So very simple. Anybody should be able to guess the answer? Come on, guys. Can you help me by hurrying up because I was. Sorry? What's the answer?
1.
1. Who is that, please?
Kwa.
Kwa. Thank you, Kwa. Okay. What's the minimum number of circuit breakers that may be tripped by the 50 BF? The minimum number. 1, 3, or 5?
1.
No. 50 BF must trip how many? No, it's more than 1.
3.
It's 3. It's 3. Because it assumes that like a bus bar fault, you trip one side of it, So to trip for the bus bar fault, we need 3. Yes, you're right. Qua, is it? Okay, what's the maximum number of circuit breakers that may be tripped by the 50 BF? Maximum? So minimum we know is 3, maximum must be?
5.
5 lah, obviously. Okay, what's the purpose of the bus separation scheme? To trip all 4 contributions? Oh, I saw some typo error. All 4 contributions after breaker failure. To trip fault current through the bus section before main relay operation. Trip bus fault current through bus section after main relay failure. So which one?
Third one.
Thank you. The third one. So there is a main protection supposed to operate, but it didn't operate. So what we do, we then have to trip the bus section. So the answer is to trip the fault current through the bus tie after the main relay has failed. Thank you. What's the maximum number of circuit breakers that may be tripped by the bus separation relay? 1, 3, or 5?
1.
Thank you. It only has as the name says, bus separation. Bus in this case only one breaker. So trip 1. Can the breaker failure operate after a bus bar fault? Yes or no? In other words, can the breaker fail during a bus bar fault? Yes or no?
Yeah, yes.
The answer is yes. Because breaker failure, any breaker can fail. Okay. Can the breaker failure trip a circuit breaker trip all 5 circuit breakers? Yes or no? It's a repeat question.
Yes.
And the answer is yes. Okay. So must the breaker failure be slower than the main protection for the substation? Yes or no? Must it be slower than the main protection?
Yes. Yes.
Yes, and the answer is yes. Must it be faster than the backup protection?
Yes.
No.
No, it must be. Yeah, it must be.
No.
Yeah, it must be. The answer is yes. Sorry. Getting myself mixed up. What type of relay is used for the 50 BF scheme? So is it a voltage? Is it the current? Is it a distance? How many answers do we need?
Current.
In this actually we need to answer the question is not quite actually what type of relays are used. So TMB uses distance, but I'm suggesting use current. So the answers are current and distance. What sort of time delay does the bus separation relay have? Instantaneous, definite time, inverse time.
Mr. Lee, your type of relay is used 50 BF is.
Oh, sorry. Okay, sorry. Read wrongly. Okay, quite right. Ong is right. Sorry, I apologize. Sometimes. Okay, the previous answer is current. Sorry, 50 BF is the current operated relay. Only 50 BS is can be maybe a distance. Sorry. Thank you, Ong. Okay, so what sort of time delay does the bus separation relay have? Instantaneous, definite time, or inverse time?
Definite time.
Definite time. Okay, the answer is definite time. Can the 50 BS scheme operate if the bus tie breaker is open?
Yes.
Can operate or not?
Yes.
Yes, the answer is
Yes.
it doesn't care. Okay. Can the bus separation scheme operate if the bus tie breaker is open? Can it operate or not? No, because I'm not likely, very unlikely that you're going to have a fault current flowing if the bus tie through the bus tie if the breaker is open. Which relay will initiate an intertrips to the upstream circuit breaker? 50 BF, bus separation, or both?
Breaker failure.
50 BF.
Only 50 BF. 50 BF
Yes.
is the only relay that initiates an intertrip. Okay, so some of you got it wrong. So some of these questions will come out. So hopefully you find this interesting. Okay, now I got three more topics to cover, and I don't know how I'm going to do it. So I'm going to have to rush through like mad. So the good news is you all ask a lot of questions. That's good. But the bad thing now, I'm now behind time now. So what type of transmission circuits fault do we have? We have faults in bus bars. We have faults in transformers are very rare. But faults in lines are very high. Okay. Fault in cables are also very rare. Okay. Why? Lines are exposed to lightning, and then you got people working underneath, and then you got people burning vegetation underneath. Okay. So in other words, For transmission and distribution lines, okay, we normally, lines only, not cables, we normally put in what they call auto reclose. But auto reclose for line, for distribution is slightly different. Okay, so because they say that 80 to 85% of line faults are transient faults. That means temporary faults, so you can close back immediately, and hopefully 80%, 85% of the time, the insulation will recover and you're okay. So we need to use auto reclose relays in transmission circuits, and we also do that on distribution circuits for 3311 kV, but we call them reclosers. So reclosers are different in that they actually have got they are built in. They are built in everything that's built in, mounted on the pole with all the deep power supply, the CTs, the relays, the reclosing mechanism, everything. So we call them reclosers. So reclosers are different from auto reclose. So auto reclose used in what we call the bigger substations. Okay. Okay. So I have to skip a lot of this lah. I just show you this. There's one line here that says here, the bottom line here. Can you see it? It says O 0.3 seconds, CO 3 minutes, and they call that the operating sequence. So you find that all circuit breakers at transmission level or distribution level have this. So what O 0.3 seconds, CO means? O means the breaker is open. It was closed, maybe it tripped. 0.3 seconds later, we are able to close it back. That's what the C means. So this is meant for auto reclose, in other words. So you close it back. What happens if it's okay? Okay, then nothing happens. But what happens if you trip again due to the same fault or different fault? So if you trip again, according to the design, this can reclose back within 3 minutes. So you're going to need a longer time to recover. But in Malaysia, we only allow a single shot. Single shot means open, close in 0.3 seconds, and if it trips again, we don't try anymore. So we have always got a single shot auto reclose. So that's what this is trying to tell you. So very quickly, what happens if you got a fault? So if you have a transmission line, distribution, we only need one auto reclose relay. But in transmission, we need two auto reclose relay because we got two sources. So we have breaker A here, breaker B there, and there's a fault. So we assume that the fault is what we call transient. So what will happen? Both will then trip. So if both trip, these will close first. AN will close, and to make sure that it's safe to close, they do what's called a check, and that check is called the deadline live bus check. So hey, my bus bar is alive, my line is dead, so we close it back. So nothing happens. Why? Because the line has insulation has recovered, but this is not closed yet. So so you have to coordinate the timing so that a little bit later, I don't know how long, maybe 1 second later, maybe 5 seconds, this will then do a check, and it will either do a live blind dead bus or more likely a synchro check. This will check that these two are in phase before we allow a reclose. And if everything is okay, we then are successfully able to close in this, and that's the end. Thank you. We have reclosed back the line. And these are typical timings. So again, you see the same thing, that there's a fault. You can see that after the fault, the trip coil is energized, the breaker contact disappear, the arc extinguishes, and then we say the breaker is fully open. Okay, you can see it? Or actually a little bit later, the breaker is fully open. So we have 3 stages of breaker operation. Now we are ready to reclose. So according to about 0.3 seconds later, we can try and close. So 0.3 seconds later, we can energize the closing coil. Okay, so that's for what you call transient fault. Okay. So I don't have time. I'll skip all this really. So what happens now? You got permanent fault. You got a permanent fault. You close back at the first end. The line will see a fault. It will re-trip. And remember, this will not try to trip a second time. Reclose a second time. So you will re-trip, and it will say lock out. Lock out means no more trying. So what happens here? This guy is set to either do a dead bus check or a synchro check, and both conditions are not satisfied. So this one will not reclose, and it will finally lock out. So we have a lockout here. After one closing from one side, then we don't try anymore. That's it. So that essentially is auto reclose. and this is for a permanent fault. Okay. Then you need the synchro check relay, and here I've given you some timings. So you can see here the first auto reclose is about 5 seconds, and the second auto reclose is half a second later. Okay. So I have to skip a lot of things here. There's a sync check relay. Again, no time really. This is related to the sync check relay. Now the interesting thing at 275 kV, at 132 kV, we do what's called a 3-phase auto reclose. So you trip on 3-phase, whether it's earth fault or phase fault, trip on 3-phase, close back on 3-phase. But at 275 kV, they do something different. They have what's called a single pole auto reclose, a single pole circuit breaker. It means that actually there are 3 circuit breakers. They are totally separated. They have different operating mechanism, different operating trip coil, different operating closing coil. So that means that if you want to, if there's an earth fault, you say, hey, A phase earth fault, let's trip the A phase. What happened? The other 2 phases can continue to carry some power. So the systems are still synchronized. Then you can say, let me try and close back the A phase. So we call it a single pole auto reclose. So 275 kV lines, 500 kV lines are fitted with single 3-pole auto reclose. So there's a switch for you to allow to say what the auto reclose you want. I have no time to ask Kennedy what the statistics are. Okay. Okay. So, and then for cables, we never allow auto reclose. So there are some lines, for example, between Labuan to mainland Sabah. Part of it is cable, part of it is submarine cable, part of OA line, no auto reclose. Okay. The questions, I don't have time to do all this really. Sorry, I got to skip really. Okay. Auto reclose is applied to transmission and distribution lines. It requires an auto reclose relay and one sync check relay at each end. Okay. And the condition for the reclosing, so live bars, deadline, live line, dead bars, or sync check at the other end. Okay, and it's a single shot. That means that if you try once and it's unsuccessful, then it locks up. Okay, any questions on auto reclosing?
There are a few questions from
okay,
Tam. So why for single pole auto reclose there is no need for any synchro check?
Oh, because Tam's question is this. In the single pole auto reclose, we do need a synchro check. Why? Because they're synchronized on the other 2 phases. The B phase and the B phase are synchronized. The C phase and the C phase are synchronized. So the A and the A phase must be synchronized. Because you cannot having 2 phase synchronized and 1 phase not synchronized. So that's the answer. Vishan?
The second question, if 3 poles trip need to synchro check before reclosing?
Yeah, 3 pole, then you'll be back to the you go back to the usual case. You do a deadline check and so on.
Yeah, that's all.
Oh, that's all.
Yeah.
Okay. Anybody, any other questions? Otherwise, okay, I got probably half an hour to finish this. So this one, hopefully, I don't know how many people are interested. We're talking about protection relay testing. So protection relays, if possible, you want to operate correctly during internal fault, but at the same time, you must operate wrongly during external fault. So what do you call it? So we say that a unit protection must be stable, and a non-unit protection must have discrimination. So we use the word stability for differential relay. We use the word coordination for overcurrent fault relays. Ideally, the two requirements, that means the two requirements are called security and reliability. Security and so ideally, if you have a fault, it's good. Why? If you have a fault, that means you prove either this relay tripped correctly, the other relay didn't trip. So it's good. But of course, in real life, you don't want it because fault can create, means got problems in your system. But in the TMD system, fault occurs all the time due to OA. OA lines fault are very, very common. I don't know whether Kennedy can give us statistics how many faults he has here at 132 or 275 kV lines a year. We can share with that. Maybe that'll be interesting. Okay. So stability. Now, how do you prove stability? How do you prove discrimination? Discrimination is a paper exercise. So you do your calculation and that's it. We can't do anything. We don't do anything. But stability depends upon the connections. And you cannot say, I check on a piece of paper, it's okay, then that's it. So in the case of differential relay, in other words, it depends upon how you connect how you install the CTs, how you wire them from the CT to the relays and so on, and how you set the relays. So to make sure that the differential relay is stable, we have to do a test. Sometimes we call it a conjunctive test, an all-in test. So it is called a stability test. We'll talk a lot about that. But there's a simpler way to do it now, and that is to do an on-load measurement. So as the load increases, before the load goes too high, you want to do an on-load test to check that the relay is stable. Why do you want to do it early? Because you don't want to say, oh, I got a generator running a 1000 megawatt generator, I'm running a 500 megawatt, and then I trip, I lost 500 megawatt of load. So you don't want that sort. So where the generator is having a very low load, typically less than 10%, you say, let me do my stability on-load check. What's the problem with this on-load check? Nobody does it. Why? Because by the time you put on load, the tester has left site already, and nobody wants to pay the extra money for him to come back to site. So nobody does it. So the only way is no choice. We have to do during commissioning this stability test. So the all kind of fault relays we do by calculation. So if you have a protection system, you must check everything: your CTs, your VTs, your connections, your meters, everything. So for the unit protection, differential protection to be stable, we need a lot of things to be correct. Everything must be correct. Your CT ratios must be correct. Your polarity must be correct. Your wiring must be correct. And then also the relay must have the correct settings. It must have the correct configuration. Okay. And it's necessary then to prove the stability by creating an external fault. What is stability? Stability means that, hey, I got a fault outside. I don't want the relay to trip. That's the word stability. The relay is stable. That means the relay didn't trip for an external fault. That's why it's called stability. So we want to prove the stability of this unit protection by simulating an external fault. So how do you simulate external fault? We have to find a way to do it. Or you take the load current during on-load measurements. So the current must flow through both sets of CTs. So a differential relay has two sets of CTs. We must have the current flowing through two sets of CTs, and we must measure one current, the current through the operating coil, because that is the current that we want. If everything is correct, that operating coil current should be very, very small. If you don't have that result, the rest of the results are useless. So ideally, that current should be zero, but in reality, maybe 1 or 2 milliamps. So we call that the relay operating coil current. Sometimes you hear the site people calling it the spill current. Okay. So the stability test usually allow, and then we say, since you have finished all this, let's go and do an internal fault. So like a bonus. So how do we do it? So you can see this transformer. So this transformer is a differential relay. So you got a CT here, it connects to a relay. This is an old wiring scheme. So now we have to apply a test voltage and we have to apply a test connection. So there are the 4 questions that you have to answer. Because if you can answer these 4 questions, then we can say you understand the concept. So number 1, where do we apply the test voltage? A, B, C, or D? Okay, remember we are going to test for an external fault. External fault, and the current must pass through the 2 CTs at the same time. So number 1, this test supply that we apply, do we apply a single phase or the 3-phase supply? Anybody want to give me an answer? Single or 3-phase supply? Vishan, yeah, I'm sure you know the answer. Vishan, no, don't want to give? Okay, Frederick, are you with us, Frederick? Yeah, Agong, I know the answer. So what's the answer, Agong? Single or 3-phase test supply?
Normally single phase.
It's a 3-phase supply. So we normally take the 3-phase supply, and the 3-phase supply is from LV supply, your 415 volt supply lah. But sometimes you got to control to a variac. So if you possible, you apply the 3-phase supply directly here. You take from the switchboard, you go to a isolator, and then you apply here. Why? You must apply before the CTs. You want the current to flow through the two CTs because you want to see what is the current flowing here. So it is applied, a three-phase apply. So where do you apply? At A, B, C, or D? Are you given the answer? The answer is at
A.
A. Thank you. So now we have current flowing through here. So it must flow through two CTs. So for the current to flow, do you have an open circuit or a short circuit at the other end?
Short.
You must short. So where do you short? Do you short at B, C, or D?
D.
Must be D. So this test is very commonly carried out. If you do an FAT for a transformer, they use this test to measure the impedance and the losses in the transformer. So they call it FAT, short circuit test. Okay. And then what do we measure? We measure this current. These are the currents we want to measure. We want to measure how much the current flowing through this. We can measure this current, the CT current, the relay current. We can measure this, but the final result we are really interested in this. Because if the polarity is wrong, these two add up, they will become very high current. If the polarity is right, this one will minus, this is a very small current. Now we've got I1 coming in, I2 going out, I1 equals to I2. The differential current in ID should be 0. So we are interested in this current, ID, the differential current, okay, the spill current, the stability current. That's what we are interested.
Engineer D.
Yes,
can I ask a question?
Sure.
Okay. The differential relay. What's your recommendation to be located at the switchgear, or is it located at the GTG control panel? You know.
You're going with the relay itself. There are two different answers. It depends on what voltage are you talking about. Jeffrey's question is, where should this relay be located? If you have what we call 275 kV substation, 122 kV substation, this will be located at a control relay panel. We always have control relay panels for all the relays. But if this is a 3311 kV transformer, this will probably be located at the 33 kV switchgear.
I want to ask, is it possible that, I have this one project, the differential relay there are two differential relay. One is provided by the GTG vendor and the other one is on the HP switchgear. I'm not sure if such a design is correct or not, What's your opinion on it?
Look, the way you said it, there's a miscoordination problem. That means that, of course, in your case, you got two relays, not so bad. I got maybe a case there are no relays. I assume the other guy is providing. I assume the other guy is providing. That case, you got a worse problem. Can you connect two relays in what do you call? Can you connect two relays? With the modern relays, it should be possible, because if you look at the wiring diagram, what it does is the current comes in, the current goes out, the current comes in, the current goes out. So you can have this CT, this one, so it is not connected like this. Okay, so you got this one goes into relay A. Let's say A1 come out A2. Then the relay, this relay got A1, A2. They can go into the second relay. Let's say call it A3, A4. Technically, it should be possible, but of course, it doesn't look very good, especially the owner looks at it. Who is the consultant who did this crazy design? It should be possible. So your question, the way I really understand it, is you have provided two differential relays. Can you wire them up? I think it should be possible. Look at the wiring diagram. With the older relays, you cannot do it, because the older relays, after this, there's a return path. But with the newer relay, the wiring is completely different.
Okay, sure.
Okay.
Thank you.
Summary of the commissioning test. So we are going to do some secondary injection tests of relays using a secondary injection test set to make sure the relay is working. How do you know the relay is working? You must have a secondary injection test set. So why do you call it secondary injection? Because it tests after the CT. It tests on the secondary side of the protection. Here I put relays, but actually we also do that for meters. How do you know the meters are working properly? Your ammeter, your kilowatt-hour meter, calibration, and so on. So we actually do for both relays and meters. Okay. We do a ratio test. So we can do a ratio test on VT, but our VT is maybe a 132 kV VT. Well, I'm going to inject 132 kV. No, we don't do that. We just inject a low voltage, maybe 415, and that's it. Okay, because if it works for 415, it should work for 132. So traditionally, we're at site. In the factory, yes, we probably will do it. But in the site, we will never do it. So we just inject at a low voltage to prove the ratio is correct. Okay, then what about CTs? CTs are more complicated. There are a lot of tests we have to do. And we are going to do a polarity check. We're going to do a magnetization curve. Okay, and we're going to do a secondary winding resistance. The secondary winding resistance is very simple. You just take any multimeter. If you really want, just take an ohm meter, your multimeter, and you just measure the secondary winding resistance. So finish up. But these two are a little bit more complicated. So we'll look at that. So CTs. So the next test we'll do is called primary injection test set. Now with the VT, we do the primary injection, but we do up to a low voltage. So in the same way, when we do CTs, my CT may be 4,000 amps. If you want to carry even a 1,000 amp test set to site, you probably need some sort of van, and you probably need about 6 very strong furnace to carry, to load and unload it. So we never do it. So we have a primary injection test set that injects a relatively low current. How low? My guess is around 300 amps. It's something that you can carry onto a plane. Check in the luggage, carry onto a plane. You can go to the site. You can do a reasonable amount of testing. So we have a primary injection test set. So that test set actually is I call it a reverse CT. It's actually a step-up CT. You inject a low current in, you get a high current out. Up to how many amps? Typically maybe about 300 amps. But you need big fat primary conductors to carry the current. So with this primary injection test, to be injected into the primary of a CT, then what do we do? So we use this primary injection test set. Number one, we prove that they are correct ratio. And number two, we prove that they're connected to the secondary equipment. So we'll do that in a little while. Okay. Then of course we have to do stability tests, but only for differential relays, using either on-load measurements or using a three-phase supply. So that's why I told you that the supply is a three-phase supply. Okay, because we have a three-phase equipment, and then of course finally we do tripping tests. So let's look at the polarity. So I won't go too much into detail. If anybody really interested, during the last session, the next session, which I hope to do next month, I will do more detail. But essentially what I tell you is this: when you apply a voltage to a transformer, in this case I show a power transformer, when you apply a voltage, the applied voltage and the induced voltage, the primary and secondary voltages are in phase. What about the current? So if you look at the load current IP and the secondary current IN, they are also in phase. But what happens within the transformer? Within the transformer, you can see these are called polarity markings. Okay, so if a current flows into this marking called A2, for example, this is A2 with a small lowercase. So if a current flows from A2 to A1, what happens here? You will say they're in phase. Look again. A current flows from A2 to A1, but on the secondary side, the current flows from IS from top to bottom. The primary current flows from top to bottom, secondary current flows from top to bottom. We say the two currents are in phase. But look at the transformer. The current that goes to the bottom comes up and goes up. So you can see within the transformer, the current on the primary side comes from top to bottom. The current from the secondary side goes from bottom to top. Sounds very strange, but that's what happens. In the load currents, IP and IS, as well as load currents, they are in phase. But within the transformer, the two currents are in opposite direction. So you have to remember that currents flow in opposite direction within transformers. And you want to know more? Please come for the next event. So So how do we do the this polarity test? So when you buy a CT, according to IEC, all CTs, all VTs are marked in this way: P2, P1, S2, S1. They are markings. Okay. So what it means is, if a current flows from, in this case not shown, if a current flows from P2 to P1, the secondary current in the transformer will flow from S1 to S2, P2 to P1, S1 to S2, opposite direction. So how do we check these markings are correct? So we then have a very simple test. So this simple test is like this. It needs, number one, a small battery. Technically speaking, if your CT is very small, 1.5 volts, usually they put about four of them in series. So maybe the 6 volts, a normal AA battery or D battery. So what we then do is we go to this, and number one, before we start, we go to put an ammeter. But this ammeter must be an analog meter, your Sunwa meter, okay, your $30 Sunwa meter. So we go and choose one side. We say, okay, and it must be set to DC milliamp. So the DC got plus and minus. So I'm going to take the plus sign. I like to connect to S1, and the minus sign I connect to S2. So then you take a battery and you connect it in the same way. If the positive is connected to 1, so I take the positive and connect to the P1. I then go and short it. So I'm applying a DC current will flow here, because this one is a very small resistance. So DC current will flow here from P1 to P2. And this will induce a current from S2 to S1 in the opposite direction for a very short while. The current flows in the opposite direction from S2 to S1, and this current will cause this meter to move forward. So we call it a kick. You move forward, and then the current will stop. Then you go back to 0. So if this moves forward, then we say, the polarity is correct when we close this contact. What happens when we break? When we break, the current will flow backward and then back to 0. So this test is called a polarity test, and we use it to check the polarity of all CTs. We can use it to test polarity of VTs and transformers also can. Okay, and in all the years, I've never heard of any CTs been what they call wrongly marked. Should never happen. So we just do it and just say, okay, CT polarity confirmed correct. But sometimes on the test result, you may see the word negative. So why negative? Because the currents are flowing in negative direction. So some of the tests that we see polarity negative. Negative, something is wrong lah. No, negative is right in this case. Now we come to magnetizing curve. So a magnetizing curve, I'm going to
engineer. The CT polarity test just now. Normally this test is done at the CT manufacturing plant, or is it after install?
Here we are talking about site testing. Everything we are talking about site testing.
Okay, good.
We are now at site, you are doing testing at site. And that's why I say, remember I told you, the VT, you cannot say I want to go and test 132 kV at site, because where are you going to get a 132 kV? Okay, you probably can, but nobody will do it. So we only do it at low voltage. In the factory, you have to do it at high voltage. That's what I told you earlier. Okay, Jeffrey? Jeffrey, is that okay?
Yes.
So now we come to this. Now, every iron core equipment have this curve, and this curve is called a magnetization curve, and the scales are the exciting voltage and the exciting current. So why do you call it exciting voltage, exciting current? Because this is a current that excites the iron core of the CT. So how we do it is essentially very simple. We take a CT, okay, we make sure that the primary circuit is open. Then we apply a voltage, and we vary this voltage through a variac, and we measure the AC voltage, AC current. So it is using a single phase variac to control the AC voltage, and then we measure the AC current, and then we get this curve. So this curve will initially show a straight line, and as you know, all iron core saturate, and this will then be where the curve, what they call the CT starts to saturate, the iron core starts to saturate. And then there's a point, they call it the knee point, and the knee point is mathematically defined as the point that a 10% increase of voltage gives rise to a 50% increase in current. It's a mathematical definition. So we want to do this. Now, why do we do this? In the good old days, we did it without understanding what we were doing. But now we understand better. Okay, so let us look at this, the significance of magnetizing curve. And to understand it, let's go to a power transformer. I'm sure a lot of you have been to a factory to do a FAT for a power transformer. Maybe it's 1000 kVA, never mind. And in there, they will actually measure losses. The losses are called the guaranteed value. And if they have a problem meeting those losses, there's a big contractual issue. So what are the two losses in a transformer? I'm not talking about CTs, not in general in transformers. So in transformers, we have two losses, and we call them the load loss and the no load loss. But I'm going to go back to an old word which nobody uses, but for the purpose of training, it's easier to understand. So the load loss, I'm going to call it by the good old name, the copper loss. Of course, nowadays we use a lot of aluminum winding, but I'm going to call it copper loss. So the load loss or the copper loss is due to the current flowing through the winding resistance. The winding must have a resistance. It carries a current. So you have an I squared R copper loss. So we call it the copper because it is a current flowing through the copper winding. And that's one loss. It's due to the current. The second loss is called the no load, but I'm going to call it the iron loss. Why iron? Because we need to excite the iron core. We need to magnetize the iron core. And it is the iron core that needs it, so therefore we call it the no load or the iron loss. And this one is done at the rated voltage. So you go and in other words, you buy a transformer. You say, hey, my transformer 11 kV step down to 415. Okay, so in the factory, they will then take the transformer, energize it at 11 kV, measure this own current. So this current must be measured when there's the secondary is open circuited. But in the case of CT, the primary that's open circuited. Okay, so you can see from here. You can see here the breaker. Okay, main breaker here open. So we have the primary side open, and the secondary side we apply a voltage to this, and then we plot this curve. Okay. So the test is done by applying this single phase voltage. We increase the voltage and we measure the current with the primary on open circuit for the CT. Okay, and it will increase, and then we go up until the knee point, and we start to saturate, and we go a little bit above there. We say, okay, we have taken our measurements. So what are the two scales? The vertical scale is the voltage. The horizontal scale is the current, and this current represents the CT error. And the higher the CT error, the higher the current, the higher the error, the higher the losses. So you try to keep it as low as possible. And the only way you can keep, one of the way to keep it low is to have a bigger iron core, which means more money. Okay. And here I've given you some notes, which I won't go through today. So any questions about this magnetizing curve? Okay, so why did I include this? So sorry, this is probably included. Okay, so it just says the magnetizing curve can be derived by injecting a voltage into the winding using a variable voltage supply, a single phase variable voltage. Okay, so we're finished with the CTs, not yet but we're finished with quite a bit. Now we come to the secondary injection test. So secondary injection test, as the name says, we're going to inject after the CT. Sorry, is there a question?
Yeah, the magnetizing test. Actually, what is the objective for the test to ensure the CT does not saturate?
No. All CTs, all iron core equipment will saturate. You cannot say I want a CT that doesn't saturate. It's technically speaking, I won't go into it because anybody interested have to come back for the next course. Essentially, a protection CT must have a high knee point voltage. Why you want to have a high knee point voltage? Because protection CTs are required to drive high fault currents. When we talk about CTs, we never look at voltage. But if you look at the American standards, they actually talk about voltage. So voltage actually is very important, but we've all forgotten about it because of IEC. So I blame IEC for not talking about voltage. So IEC, actually there is a voltage because you want to drive a high fault current. How high is the fault current? 10 times, 20 times through impedance. And to drive a current through an impedance, we must have a voltage. So a protection CT must have a high enough voltage. Before it saturates, you can drive the current. And you want to know more, then you come back for the next. But what about metering? Metering is opposite. We want a low voltage. But in reality, metering CTs may not have a low voltage because of other complications. Okay, I won't go into detail into that for today. Jeffrey?
Okay, sure.
And if you really want, there'll be formulas for you to check, hey, I got a class 5P20 15 VA CT. How do I know this CT is able to drive that current? So please come back for the next course. Okay, any other questions? Okay, now we come to secondary injection. So as the name tells you, it is testing the relay or the meter on the secondary side. That means we assume that the CTs, the VTs are correct. So we just inject after the CTs. So to do that, we need a secondary injection test set. Now, secondary injection can be very, very simple. You can have one, probably in a small box, smaller than probably your lunch, not lunch box, a small box. Probably say 2.5 kg Milo-tin, maybe less than double the size. You can carry with you with one hand. Okay, and what can that do? You can create a single phase voltage, a single phase current, and you then inject that voltage or current into the relay. You can see here the relay test points. So you inject it, and then you can go and test and say, hey, when I increase the current, there come a point, this relay gives me a signal that it has tripped and operated. Then when it trip operated, you can send a signal back. The relay trip. So you can see this is a trip contact. So the trip contact, you can see the word trip. So I can go to here and then stop a timer. So what I will do is, for example, I have an overcurrent relay. I will test it at say 2 times the rated current. So I go and adjust it to 2 times the rated current. Switch it off. Okay, connect everything and switch it off. Then press the start button. So when the button starts, then this relay, the test set will set a timer. You inject a current, set the timer until this relay trips. Then they send the signal stop. Then we measure this, read this timing. That's all. So a secondary injection test can be very simple. As I say, like a Milo-tin, a bit bigger, carry with you, and that's it. Walk around with it. But it can also be very expensive. I don't. Sorry?
Okay, sorry. Allow me to just break for a while because I missed stop recording. Short while.
Okay, let me know.
Okay, should be ready.
Okay. Now, so this is a simple test set. Maybe call it a couple of thousand. Maybe, I don't know, maybe 10,000. I have no idea. But you can also have a very expensive test set, what I call the Ferrari test set. And this Ferrari test set, one set of it can buy you half a Mercedes. We're talking about 200, 300,000. That one, there's one brand called, a brand that you will know the name very well. They call Omicron. It's an Omicron test set. So we have a very expensive test set, and that one is a fantastic test set. Okay, I'll show you a little bit more. But before you go into test sets, I want to talk about testing facilities. So you have a relay. So what we do is we wire them to terminal test, what we call test blocks. So this is a test block. Okay, you can see the test block is here like this. And what you can do is you can then take a handle like this, connect it to a test set, and then plug it in, and then you can inject. So this is the ABB model. Okay, and I'm told this is a very expensive unit. I don't know how much it costs, but I was told it's quite expensive. And I was told in this one is made of plastic, so the plastic parts can fail, but still a very expensive test set. So this is a secondary injection testing facility. So all relays should be wired through test terminal blocks, or here in this case, ABB call it a test plug. Okay, a test switch. They call it a test switch. Okay, so these are the ones at your relay panel. And then to do the testing, we then use this test plug. And this test plug must have some facilities. When you plug it in, the CTs must short itself, because you don't open circuit CTs. So it must short the CTs, and you must open circuit the VTs, and you must also isolate the trip, because you don't want to, when you're testing, when cause a bus bar trip. So that's what this is doing. Okay, so I just show you a few of these. So you can see in this case, I won't go into detail. We not only have that, we can have a thing called emitter, what they call it, emitter test plug. So you can plug it in, and you can see the CT connection shorting itself. Okay, you can see that these are the CT connections. You can see under normal condition, this one is going to the relay. Okay, it comes in and it goes to the relay. Okay, you can see the relay is here. But when you can plug in this test plug, the CT shorts itself. So the CT comes in, it's shorted. And then you can then apply a test current here. So that's what this test, this one is. So essentially, then there's another one for to isolate DC. Okay, and you can see again the 3 tau contact. So they have one for the they call it the blocking trip circuit. So you want the trip circuit to be energized. You can see the CT here. So when you plug it in, it will switch to the shorting position. And this one for VT, slightly different from the one for the blocking. Okay. So then of course, as I say, you have the Ferrari test set. So this Ferrari test set can do a lot of things. You can generate 2 sets of 3-phase current, 1 set of 3-phase voltages. You can control the frequency, you can control the magnitude, you can control the phase angle of the output quantities. You can be synchronized through a GPS, because I need to do simultaneous testing at 2 ends of a line, which I'll show you in a while. So you use a GPS and so on. And the other nice thing is it can be automated. I'll show you what I mean, automated for testing, especially of very complicated relays like distance relays. Okay. And you can do other tests, like you can do bias characteristic tests, you can do harmonic restraint tests, and you can also do what's called secondary stability test. And you can do polarity test, the polar plot of distance relays. I'll show you some of this a bit later. Okay. So so here you can see this is the one they call it the test switch. So here is where you will plug it in. So when you plug it in, okay, the relay is here, the CT is there. So you short the CTs, now you inject current into the relay. So your CT ratios, okay, so you insert a test plug here for the purpose of testing, and these are the test terminals. Okay, but I call it test terminal block. Maybe you can call it test switch. A single phase current, and you then inject that voltage of current. Sorry, is there a question? Is there a question? No question? I heard something about single phase current or voltage. What you want to inject is up to you. For example, if this is a voltage operated relay, then you inject a voltage. Because when you do this, let's say your transformer is alive. So there is a voltage. Normally we don't do it alive, but let's say there's a voltage and you want to test it. So when you plug the test set in, it will open circuit this. So the voltage is coming here and it's going to the relay. So when you plug in, it will open this. So your voltage is still there, and then you connect your relay test set to these 2 points, inject the voltage, like what is shown here. Okay, what is shown here. Okay. So now we come to distance relays. So distance relays are very complicated, and distance relays, okay, I'll just show you this. So this is a distance relay. This is a quadrilateral distance relay. So what do you want to do? In the good old days, essentially we only test at one point, test at this, and maybe once in 2 years we test for a few other points. But now, first of all, how many distance relays do we have? How many zones do we have? We have 3 zones. So we have zone 1, zone 2, in this case zone 3 is not shown. So if I want to test for all this, wow, how many points do I have to test? Let's say I test at every 15 degrees. Wow, I probably got something like 10, 15 points to test. And can I do it? In the good old days, do we do it manually? But nowadays we do it automatically. So what we do, we program the relay and say, okay, I want you to test at angle, say -15, 0, 15, and so on. I will set the current probably 1 amp, and then you go and test. So we just program, plug the relay in, and then go for coffee, come back, everything is in your computer. You cannot cheat. You cannot say, I've tested it. Why? There you can see this handwritten report. You cannot cheat because it is there. So this is called polar plot. And if without this automatic test set, oh sorry, there are 3 zones. Sorry, I didn't see. There are 3 zones. You can see there's zone 1, zone 2, and zone 3. And how much time do you need? If you're doing it manually, you need a lot. So how do we do it? In the good old days, what we then do is we inject a current and we put the voltage high. For example, hey, my relay is 20 ohms. Let's say I can put the voltage at 1 amp, 30 volts. So too high, and then I reduce the voltage until this one trips. Okay, zone 3 trip. Reduce further, maybe zone 2 trip. Reduce further, zone 1 trip. So that's how we used to do it in the good old days. Now, as I say, all this automatic test set. So, now any questions before I talk about primary injection? Surprise, no questions. So primary injection is we're going to test into the primary of the circuit. We have tested the CTs are okay, we have tested that the VTs are okay, we have tested the relays are okay. Now we're going to make sure that everything is okay. We need to do a primary injection. We only do primary injection for CTs. We don't do primary injection for VTs. So, so this primary injection test set, we need this in the test set. We need to have a control supply. Okay. Usually it's a single phase supply. Okay, for the you can use it for various things like to measure the impedance or the stability, and you can have a load current. So we can also use load current. So the one that we're going to spend now is talking about this primary injection test set. So the primary injection test set essentially is a step-up CT. You inject a low current and you get a high current out of it. Okay, and typically I put here is about 500 amps. My guess will be closer to 300 amps, and this is a high current at low voltage. Okay, the VA is the same. So if you want to see this VT, let me show it to you. So you can see this is a CT, and you can see here what it says here, 250 volts. This is the input, 250 volts, and the output of this, there are 4 outputs. Each output is 10 volts, and how many amps? 40 amps input, and I think it's 250 amps output. I think 250 amps output. Yeah, 250 amps. No, it's 200. Then now say the VA lah. This is a 10 VA. So 40 amps multiplied 250 volts multiplied by 40 amps, or 40 volts multiplied by 250 amps. Okay, so no, by more than that. I can't remember. My mind not working. So you can see that this one can create high voltage. So this high voltage can go out, and then you can apply to a test set. Okay, so what test can you do? Well, there are 2 tests you can do. It's a single phase quantity. So you can only do a single phase test. But this can be a single phase earth fault test or a single phase face-to-face fault test. So you can see here, this is my test set. So I got 2 outputs. So I'm going to test into this relay. So what's the easiest way to do it? What's the easiest way to do it? And we need a big fat conductor because it must carry a few hundred amps. So you need a big fat conductor to carry this. So my CT is 2000 to 1. So I want to inject 2000. Sorry, we're not going to inject 2000. Why? The test set required to be too big, too difficult. So I'm going to inject a low current, maybe 200-300 amps. So what do? The simplest way is you go to this circuit, you go and close the earthing switch. You can see the earthing switch. This is closed. So that's one test point. You then go to your primary injection test set, earth it. And all you then need to do is to go here and do one connection. So you do the connection, and I'm injecting a current here into the A phase, into the earth, come back to here. So I'm injecting an A phase current, single phase port. So what do? I measure the CT current. A phase must be having a current. B phase, C phase, no current. So I know it's correct. So that takes care of earth fault. Now I want to do another one for face-to-face fault. So how do I do for face-to-face fault? So what you then do is, now instead of connecting to this to earth now, we take this and we connect it here. So here now we need two leads. So one lead is connected to A phase, one lead is connected to the B phase. I want to inject an AB fault. So I have a current coming here, go to the earth switch, goes to this earth, come back to here, and then go back. You can see the connection. A phase goes to the earth, goes back to the B phase. So with this single phase injection test set, I can do a earth fault, I can do a face-to-face fault. Why do I need to do a face-to-face fault? I'll tell you in later on. And then these are test blocks. And from there, in the good old days, we use a lot of this. So you imagine that this is the ABB test switch that you have. So you remember I told you that there are those little test plugs. Remember I told you this? So you can go and put in this. So when you put in this, you actually can measure the current. It says test plug for which disconnect the relay and connect it to the test lead. So you actually can do this. Okay. Sorry, actually, okay. Sorry, I think I'm not quite. But you actually can measure the current, but we don't need to. Why? Why is very simple. Because we can go to the relay itself and go say, hey, A phase, what's the current? B phase, C phase. So no need to make these measurements. In the good old days, we have to. Because in the good old days, the mechanical relays got no meters. Now we have meters in the relay. So just go and measure the relay itself to solve all the problem. Okay. And then this one measures the neutral current. You got the A phase, B phase, C phase, and the last one measures the neutral current. And this neutral current can be very important. Okay. So any questions? I'm surprised there are no questions. Okay. So this is all more or less the same as the previous one. But I want to tell you one thing. So, okay, you can see the primary injection test set. So we have primary injection test set. We have a CT that will tell us how much current we're injecting. So let's start with a single phase. So you can see in this case, I'm going to inject into the B phase. So my test set, I didn't use the earth switch now. You can see I got a connection here. It goes to the B phase and come back to the test set. So we're injecting into the B phase, and then we go to the relay on the B phase. Are you measuring a B phase current? Yes. Do you want to measure the neutral current? If you want, you can measure the neutral current. So and the overcurrent relay, the B phase overcurrent relay should operate. For relay should also operate, or at least see a current. So we do that for technically speaking. I need to do only for one CT, but usually we do for all three, I imagine. Now we come to the other one for face to face. So we're going to use the same test set, a single phase test set for the earth fault and the face to face. So you can see in this case, the test set, I'm going to connect to the A phase. Then it goes to the B phase. I short this part, then come back to the B phase. So it goes into A, come out as a B, come back to the test set. So what do we measure? You say I measure the A phase and the B phase. But one very important measurement is to measure the neutral. Why? If the polarity of this is wrong, then this will give us double the current. So in other words, the current should be IA minus IB. Because one going will come out. So this should be 0. IA minus IB is 0. Because this relay actually measures IA plus IB plus IN. But IA and IB are in opposite direction. So IA minus IB should be 0. Unless the CT polarity is wrong, then this becomes IA plus IB. So this will tell us, in a way, checking the polarity. Okay, so there will be some question related to this. We are going to use a primary injection test set to do this. It's a single phase primary injection test set, AC input current, but it can be used of earth fault, single phase earth fault. It can be used of face to face fault. Of course, you can't do a three phase. So that's primary injection. So we then do for all the CTs. We check, hey, I check this phase, I measure there, and maybe you shot the other CTs, because otherwise maybe the wrong CT is going there. So you check on the A phase. I got 3 CTs. I shot the other 2. The first one must go to the overcurrent relay. So I go to overcurrent relay. Yes. And maybe you like to look at the other 2, maybe the meters and so on. Hey, no current. Correct. Confirm correct. Okay. So that's called primary injection test. Now we come to the last part, which is a stability test, which we need for all the differential relays. So essentially, the stability test is one, as I told you at the beginning, we apply usually either a single phase or a 3-phase. If it's a transformer, we apply a 3-phase voltage. If it is a cable, maybe we apply a single phase. So we are going to apply a test voltage here. If it's single, can be 3-phase, but transformer is a 3-phase. And you can see we're going to inject a current passing through the CT on the primary side. This is a transformer, CT to the secondary side, and we're going to create a short circuit here. So is it an internal or an external fault? It's an external fault. A current is passing through 2 CTs. So we don't want the relay to trip. So what do we measure? The most important measurement we make is this one. You can see the relay, this is the most important measurement. So we check that, the relay here, the current here is very small. Okay, we can maybe look at this CT and this CT, this one, maybe 100 milliamp, 100 milliamp, but this is 0. If anything is wrong, then this will be 100, this may be 200. Then something is wrong with the polarity. The relay is not stable. So we call this a stability test. We check whether the CTs are connected correctly. Okay, and then usually as a bonus, we then do an internal fault. So we take this test point, we shift it here. This time, this CT will see a current, this CT will not see a current. So the CT current will flow through here, and the relay will say, hey, I see a high fault current. So essentially, that's what we do. Okay. So now, in place of this, we can use a load measurement. I told you many times. But we cannot do load measurements for restricted fault, because restricted fault requires a phase CT and a neutral CT. And the neutral CT will not carry any current during load. So for restricted fault, we need a test, which we'll look at in a little while. So any questions here? So in this case, you can see we are doing the essential what I showed you earlier, and that is there's a test point here, and you apply a voltage here, and then the current passing through the 2 cell CTs, and we are looking at this current. We can measure the other current for information, but this is a current we're interested in, and this current should be very, very small, maybe less than 1% of this current. Then once we finish, then what we do as a bonus, let's take this and shift it here. Okay, then we do an internal fault. Now the current passes through 1 CT. This time this current should be equal to this current. Okay. So these are typical test results that you will see. I'm behind time, so I won't go into it. So you can see in this case, this is an external fault, or it may be a load current. You can see I1, I2 are the 2 currents. The CT current, 50 milliamp, 50 milliamp is an external fault. So what is ID? ID is a differential relay current. ID is I1 minus I2 should be 0. So this is the most important part. The relay operating coil current. Okay. And then we do an internal fault. Internal fault, they go current here, no current here. So this one equals to this one because I2 is 0. So I1 minus I2 is equal to I1, which is this one. So 50 equals 50. Okay. And then of course, if you got a wrong connection, are there cases that CTs are wrongly connected? Yes, there have been cases. So if you have a wrong connection, there'll be 50-50 like before, but this one is 100. There's something wrong. Okay. For practical aspects of stability test, so the connections can be. This is just. I don't take enough time now. But how do you do this test? So among other things, we can do you can use the earthing switch as a test point. We can use this point either inject a current, or you can inject a current here, or we go and earth it as a test point. And this one very easy with AIS, air insulated, but with GIS it's a bit more complicated. GIS, they don't, the earthing switch, we may have a problem because how do you inject a current here? So we may need a special plug to inject it here. You can see. So, and if the CT is here, then we have a problem. How to inject in here? So when you do all these tests, you got to consider all this. GIS can be very complicated. This is for the REF relays. So REF relay, you got to do a test where a current flows. You cannot do a load measurement because under the load measurement, the neutral current, neutral or no current. So you have to make sure the polarity between this and this is correct. So you then inject a single phase. So you come here, okay, and then you jumper this because you cannot pass through a transformer. So you jumper it. So A phase, then from phase jumper to neutral. So a current flows to the phase, a current flows to the neutral CT, and we then have this current. So that's one way to do it. And there's another way to do it where we use what is called zero sequence test arrangement. So this one's a little bit more complicated, but it can be done. Anybody interested, we can talk about it later. Busbar protection are the most complicated. Why? Because you got to prove that the relay is stable for every CT, every pair of CT. So you're going to come here and inject in the CT number 1, come on CT number 2. This is stable. So you can see that we are making a lot of measurements, and the one that we are most interested in is this measurement. Okay, then suppose you got 10 CTs. Now you must repeat between CT2 to CT3. Repeat between CT3 and CT4. So you have to do this many times. This stability. The other problem with busbar protection is we have an overlapping zone. Remember? So how do you test it? So what you can then do is you can inject a current here and say I got a current coming here, and then both the discriminating zone for this side and that side should operate. Very simple, right? You go and create a short circuit here, inject a current here, come out here. So it passes through this CT and this CT. So this one will operate one relay, this one will operate another relay. Very simple, but in practice, very difficult to do it if you have GIS. Why? Because this point is not accessible. There's no way for you to apply a test connection. So you're probably going to find some other ways to do it. Okay. So as I said, you have got various ways: primary, on load, and then nowadays remember the high end test set. Okay, sorry. What about if you got a cable, you got overhead line? So I got this. This line may be 100 kilometers apart. So how do I inject? So technically speaking, I will have to inject a current here and come out here. There may be a problem with overhead lines. Why? Because nowadays there's so much induced voltage on this line, you cannot go and touch it. The moment you take off the earth, the voltage is very high, maybe a couple of thousand volts, so we can't do it. So what would they then do for current differential relay is they have what's called an end-to-end test. You can see here they have two test sets, and they're going to go here. Okay, I'm going to apply you got to program the relays, all the program the test set. So you program the test set. Hey, I'm going to apply A phase over current, let's say 3 amps for say 100 milliseconds. So 3 amps 100 milliseconds, 3 amps 100 milliseconds. So all you have to do is to find somebody and say, okay, let's start the test. Bam! Impossible to do it. Why? Because you cannot coordinate the timing. You tried. I switch it on before you can switch on. This is like trip ready. Of course, I can go and do other tricks like delay. So what they then do? They then go and set up a GPS. So they go to this relay and set up a GPS, establish a connection with this. And this GPS is connected to the test set. So what we then do? Okay, when we test and switch on this test set will send a signal through the GPS to the other test set and test exactly at the same time within microsecond difference. That's how accurate it must be. So they call it an end-to-end test. Of course, we're not testing the CT primary circuit. So we assume that the CT primary circuit is okay. So we're just testing only the relay connections only. Okay. So this is called an end-to-end test. Okay, so and this GPS, by the way, can be quite expensive. One of these unit can cost you, I was told, about 10,000 ringgit or even more. We have reached the end. So what are the key points? So the key points we have learned is commissioning test for CTs. We have magnetizing characteristic. We have polarity test to prove polarity markings are correct. We have primary injection to prove that CTs have the correct ratio and are connected to the right equipment. Secondary injection test to prove that the relays are working correctly. Okay, stability test of differential relays to prove stability during external fault. Again, I don't have enough time to go through this, so I'll leave you to go through this. If any of you are interested, there are a lot of free technical books. So this is the one that I used to send you the passport protection for the differential for the double bus bar. So it's called MPAG. So you just go and Google for MPAG, you should be able to find it. There's a protection guide, a very simple one. Anybody interested, you can't find it, let me know. And then on the internet, GE has got various what they call videos. So they call it FMPR. Just Google for GE FMPR, you should be able to find the videos. Okay. So we are talking about site. When you're doing site, there's always a danger. So I like you to be careful. So beware of electricity, safety always for everyone. And then don't be like this old man who said, I worked for 30 years and then only one accident. And one accident is too many. Okay, so that's the end of the notes. We are exactly 1 o'clock. So I want to do a quiz. So anybody, what we call, got any questions before I do the quiz?
Yeah, Mr. Liam Kennedy here.
Hey, Kennedy, yes.
Yes, just now you mentioned that regarding the LV transformer paralleling. Yes, you said it's correct. Normally at the LV, we keep it parallel. We only open it if there's a high fault current or it is above firm. Above firm means if one transformer trip, the other one is overloaded. So that is the reason we keep it open if required.
Okay. Nowadays, what TNB does is, the latest, I don't know about earlier one, the transformers are designed to carry 150% current, I think for 2 hours, something like that. I can't remember.
Yes, correct. Yeah.
So there is some leeway for you to play with lah. But yes, you can take advantage of that lah. Okay.
Correct.
You're not asking a question, it's just a comment. Am I right?
Yeah, the comment that earlier Mr. Heng, I think, he mentioned that he asked why we always.
Okay, while waiting for the question, so what I'd like you to do is to do the test, and I want you to log in. This will probably take another half an hour. Okay, so can you start? The first part is the repeat lah. Okay, can you see the login? This is the same address as before, so I just want to do very quickly the same test and a bit more, and then after that the second test. So okay, so I'm going to start my call while we're waiting for the other questions. Okay, so can you all start logging in? Okay, I think I may have to go until here before. Yeah. So okay. So can you all start logging in? So it's ahaslide.com/7cpx3. Okay. So thank you. And Kelvin, thank you for being the number one. Okay. So the first part is a repeat. The second part, first 8 questions. The second part, I think next 10 questions are new. Okay. Any other questions or comments? We can try to discuss during the logging in.
Mr. Lee, Chung here.
Hold on, Chung.
Okay.
Yes, John. Please go ahead.
Yeah, for the online load test, is it just to confirm or verify the stability of the relay? What I see what they did normally, they get some current flow to it, then they measure the relay current and angle, make sure everything in order. That's the purpose.
Okay. There are various load tests you can do lah. Let's start with the meter lah. Easier, kilowatt meter. For example, let's say we got this energy meter. So what must TMB do? TMB must go and look at it and see that, for example, it's measuring in the right direction. Very simple. So you then go and look at, hey, my three phases, the voltages, now are they roughly 110 volts? Are they 120 degrees apart? And then I look at the three currents. Are they about equal? Are they lagging the phase voltage by the right angle? Okay. So, and then finally, I look at the direction of the meter. And the angle and the direction. In those days, of course, we have you can see the meter, the mechanical movement. We look at it. Hey, the meter is moving in a forward direction. Okay, and then you don't have to do any calibration. So I would do that, for example, in the good old days. So in this case, for a meter, I would do the same thing. I would go and look at the voltages, confirm voltages are 120 degrees apart, reasonably well balanced, both currents well balanced, and also lagging by the consistent angle. And then finally, look at the meter. Now, and then if you want to, I don't think you need to. I calculate the power factor manually. I look at the meter, is it accurate? And finally, the direction of the meter. So that's what I would do with the meter. Okay. Now, with the relay, I would probably do the same thing. I would, for example, let's say a transformer differential relay. I will look at the current. Okay, the three currents, are they well balanced? Secondary currents, are they well balanced? Can I check? Because the values are usually, if I remember, I may be wrong, Chong. Do you remember the value, whether the CT current, are they given in primary or secondary values? Okay.
I think it's secondary or most of the delay.
Even if it's given primary or secondary, so you can do your own calculation. Hey, this one, if I go and consider the CT ratio, hey, is it correct or not? For example, let's say in one case you have a dual, in one side you have a dual ratio CT. Hey, am I getting the result logical? One side getting 0.5 amps, the other side getting only 0.2 amps, right? Something is wrong. How can so much difference? So you look at a result, whether they make sense. And of course, the angles between the currents and so on. And finally, you look at the spill current, the operating coil current. That's the most important part. But I kept it last because you will do your homework first. And everything is okay. Then look at the last part. Different current is very small, for 1% or 1%. That should be okay. So I would look at it in the sense that look at everything simple. And then finally, you record everything. You record it down for that. See thing. That's what I would do. Okay. And then, of course, the meter, you probably have, in the relay, probably a lot of metering functions, whether you want to go check the metering functions are logical, so on. You can do all that. Up to you to see how far you want to go. But for differential relay, as I said, obviously, the stability, the operating coil current, that's the most important thing. So, as I said, you always try other things. Okay. Oh, I need 41 people. Any other? Chong, have I answered your question?
Yeah. Thank you.
Okay. Any no more people coming in because I'm in a hurry So okay. I think you seem to. I'm very surprised on it. Wayne, how many people have you got?
We have 81.
No. How many participants? Sorry.
In the meeting, there are 81.
Oh, 81. Sorry, I heard 81. Okay, okay. So I'll go back and do some revisions first. So number one, the first thing is if you see a yellow slide, that means you need two answers. Please remember that. And if you can give less than one answer, less than two answers. But if you give more, I think there'll be some problem in the marking. So this is a repeat of what I told you. Just a quick revision before we start lah. So this is your H arrangement, okay, with 2 incomers, 2 outgoing feeders, 1 bus section, and this. And if you parallel this, then obviously you got current coming this way, you got current coming this way, and you got fault current flowing through the bus section. So that's you must bear in mind. The next one, of course, is the what we call the bus bar protection. So this bar protection is for not only the H arrangement, but it has got a bus coupler. And remember the 1, 2, 3, 4 I told you. So it need 1 check zone, 2 overlapping zones. So where the overlapping zone, there's 1 here, there's 1 here. Okay. 3 discriminating zones because you have 3 sections of the bus bar. 1 here, a main 1, main 2, and then you got the reserve. And a total of 4 relays. Why? Because you got 3 discriminating zone plus 1 check zone. So 1, 2, 3, 4 lah. Next one is this is a summation CT, summation transformer. So this one is pilot wire relay. They're the only one they use this. So remember, pilot wire relays are the only equipment they use this summation transformer. That's one of the questions. So it's a 3-in-1 summation. You take all the three currents, add them up in such a way that you can detect all sorts of faults using one protection element. So you put in one relay here. That relay is able to measure A phase, B phase, C phase, all phases, and all 3 phase fault. And to do that, you need these unequal multiplying factors. Okay. Okay. Now I'm going to start. Okay, so 41 people. Okay. So thank you for those who have. Okay, I'm going to start. So the first part is I thought, how come? Okay lah. Somehow I missed question 1. Never mind. We'll just continue. So the communication link for a current differential relay consists of, it will be a very simple one. I think everybody got it correct the last time. Okay, is it a copper wire? Is it optical fiber? Is it radio link? Is it a microwave link? Or is it a pilot wire? So copper wire and pilot wire are the same thing now. Okay, 3, 2, 1. Okay, everybody got it correct. Yes, this is the one everybody gets correct. Okay, very good. So okay, we missed question 1. Never mind lah. So that a lot of people get correct lah. Okay. So the next one. Okay, when the communication link fails, the current differential relay. Well, I need 2 answers. What are the 2 answers? Will it always trip during any internal or external fault? Will it be unstable during any external fault? Will it not operate during any internal or external fault? Or can it be programmed to activate zone 1? Okay, very quickly. And the answer I wanted was number 4 and number 5. So most of you are correct. By the way, in the notes also tell you for RE projects, which I didn't highlight. For RE projects, distribution people, what they do is if the pilot wire fails, they actually trip the whole 2 circuit breakers. So you can see that transmission and distribution have 2 different practice. So in the case of transmission, if the link fails, we do one of these. But in the case of distribution, if it fails, they will trip I'm not a 33 kV lah. They will trip both sides. Okay. Okay, question 4. Okay, so which of the 4 statements, which one of the four statements is true? Only one. A current differential relay can operate only as a backup. A current differential relay can operate both as a main as a backup. A current differential relay can operate without its communication link. A distance relay cannot operate without its communication link. And the current differential relay can operate only as a main. So one answer. So I've extended the time because the last time I found out, like, even I was under stress lah. Okay, and the answer I wanted was number 5. Some of you gave me a wrong answer, quite a bit. Never mind. Okay, so the answer I wanted was number 5. That is, a current differential relay is only a main. It cannot be a member. Is a differential relay. All differential relay only act as main protection. So if you say can operate as both main and backup, sorry, you are wrong. Okay, leadership. Okay, this one. Oh, okay. We got 3 questions. So far, okay. Oh, now I got a new person, Sleepy. Okay. Oh, Muiz. Okay, very good. I don't know who is KO, obviously. Okay, let's go to question 5. So all these are repeat questions. Up to question 8, they are repeat. Which 2 of the following statements are true of a distance relay? So you got about 38 seconds left. It is a non-directional relay. It has a minimum of 3 zones. The relay characteristic is shown on the VI or PQ plane. The relay setting are in volts and amps. Zone 1 is set to overreach, and then zone 1 and zone 2 normally have circular, Moore or quadrilateral characteristics. I want 2 answers. You got 5 seconds left to answer. So the answer, most of you are correct, is number 2 and number 5. A few gave number 6. A few of you say that the relay setting is in impedance. Remember, it's an impedance set. It's an impedance relay. So it's set in ohms. The distance relay. Distance cannot be given in volts and amps. Okay. Some of you say it is what they call is a non-directional. It's a directional relay. There are 2 relays that are looking at each other. So technically speaking, zone 1 and zone 2 doesn't protect the reverse side. Otherwise, you forward line is looking protecting the line, is protecting the line at the back. It's not possible to set it. And number 4, this one here, you say the distance. Okay, the relay settings are in volts and amps, are wrong. Okay, the impedance, the characteristic is shown on the RX plane, not VI plane. And zone 1 is an underreaching. Zone 1 is set to less than 100% of the line, 80%. Okay, let's move to the next one. Okay, question 6. Okay, the total number of discriminating zones. Say, remember 1, 2, 3, 4. So how many discriminating zones? So you have 0, 2, 3, 4, 5. So now you're going to make a guess where is 1, 2. Remember I told you 1, 2, 3, 4. So is it 1 is not there, 5 is not there, was not there. So it must be 2, 3, and 4. One of these. So which one? Discriminating zones. There was a slide I showed you right at the beginning. Okay, 5, 4, 3. So whoever get correct, and the answer is 3. Remember, there are some of you gave me 2. Okay, there are 2 and 4. Okay, and if somebody gave me, I just told you 5, not the answer, because 2, 3, 4. So the answer is 3. Why? Because the main bus bar is divided into left and right, and then your reserve bus. So there are 3 discriminating zones. Okay. Okay, that's total should be 20 at this moment. So some of you already saw some mark. So PPH, YY, X. Oh, Wing Xiao, very good. Muiz, Muiz still doing very well. Ho must be from Sabah, I think. Okay. Question 7. So we have 2 answers. So again, this for the busbar protection. Which of the following 2 statements are true of the high impedance busbar protection for a PMB 132 kV substation shown? So again, the 1, 2, 3, 4. Does it have 3 check zones? Does it have a total of 3 overlapping zones? 2 out of 2 tripping arrangement, and failure of check zone will disable the whole protection. On two answers. Three, two, one. And the answers I wanted was, okay, most of it correct. That it has a 2 out of 2 tripping arrangement. And if the check zone fails, you have no more protection. O is sometimes called an overall check zone. So if you say that it has 3 check zones, it's only 1. And if you say that there are 3 overlapping, there are only 2. Okay, so some of you lost marks. Okay, question 8. Okay, this is the last of the repeat questions. Which of the following are well protected? Well protected means is either within line, zone 1 or zone 2, trip reasonably fast, of a backup distance protection of a transmission line. External line fault, the next line. Downstream busbar fault, the fault that's at the end of the line. Okay, downstream means in the forward direction. Upstream busbar fault means the fault at the back, the busbar at the back, the nearby fault, nearby busbar, or downstream transmission transformer fault, and the last one, internal line fault. So I want 2 answers. So what are the 2 answers? Okay, the answer I wanted was number 2, downstream busbar fault. This in the forward direction. And the one that was very well answered was the internal line fault. It covers 100% of the line. Zone 1 and zone 2 will cover more than 100% of the line. So that was well answered. External line faults, remember the zone 2 only covers up to 120% of the line. So you cannot cover the whole of the next line. And you cannot cover reverse busbar fault. Reverse busbar is seen by zone 3, okay, which is not very good. And it also cannot cover a transformer, downstream transformer fault because again of impedance. Okay, that was the end of the repeat questions. So, okay, so there should be 28 marks by now. So some of you lost a bit of marks. Some of you are still doing very well. Okay, these are the new questions. So the next one refers to the summation transformer. So I told you, only one relay uses a summation transformer. I mentioned that just before we began. Which relay uses a summation transformer? Is it the overcurrent fault relay? Is it the pilot wire relay? Is it a high impedance relay? Restricted fault relay? Busbar protection? Distance relay? I told you at the beginning, before we started, I showed you one of the slides. And I told you the answer will come out. So which relay uses a summation transformer? The only relay that uses a summation transformer. Okay. 3, 2, 1. And the answer is, a lot of people got correct. 31. Few of you got it as overcurrent. Overcurrent, we don't have a summation transformer. And busbar, also no summation. Distance relay, no summation. So 31 uses a summation transformer. And the next one is also related to this summation transformer for pilot wire. So which 2 of the following statements are true? This is a little bit more difficult. Which statements are true of a pilot wire relay with a summation transformer? It cannot detect balanced 3-phase fault. It has the same sensitivity for all earth faults. The A phase has the highest sensitivity, that means the most sensitive. Highest means the most sensitive, lowest operating current. It has 3 operating coils. We need 3 pairs of pilot wire, and the lowest sensitivity is for the AB and BC fault. Okay, so which are the 2 answers? Now you can see all sort of questions coming out. sorry, I gave wrong answer. Okay, the first one is wrong. It has the same sensitivity. That's wrong. So this one is under the mistake. Sorry. Okay. The third one is correct. The A phase has the highest sensitivity, the most sensitive. It has 3 operating coil. No, only 1 operating coil. Remember, summation transformer. It needs 3 pairs of wire. No. And the lowest sensitivity is for the AB and BC. So it actually should be 1 and the last one. Sorry, my apologies. I checked it last night and I still made a mistake. Okay. Okay, so this is a halfway mark. So, okay, we should have 36 marks. Wow, some of you still doing very well. 32, 32, 30. Okay. Oh, Win is still also doing well. Okay, so now we move to the second part. Okay, so this second part, I'm going to do a revision again. So, a 5 circuit breaker H arrangement has 5 50 DF relays. So, you have 5. Each one, every circuit has its own circuit breaker failure. And this will trip 3 or 5 circuit breakers, depending on where the fault is. It will operate if the relay trips, but the breaker fails to open. Okay, there is only one bus separation relay at the bus tie circuit breaker. I'm assuming that I need the overcurrent relay. It will operate after the main protection fails to trip during an internal fault. It will split the system to save half the system by switching off the bus tie circuit breaker. Okay, both are time delayed. Okay, they're current operated. The nodes I have and they are set slower than the main protection, but faster than the backup. So that's the first one. The second one, auto reclosing, is used for transmission and distribution lines. A transmission line requires 1 auto reclose relay and 1 synchro check relay at each end. Distribution only need one end, the other end no need, because distribution we don't expect the supply to come back unless it's a special case. Okay, so we have a live bus deadline check for the first. We must say the bus is alive, but the line is dead, so we do the first closing. The second closing at the other end, probably the line is alive and the bus may be dead, or the bus may be alive. So you can do a live bus deadline before the closing of the second breaker, or we do a synchro check. Okay, if there's a parallel feeder or there's some other what we call supply, and it's a single shot, that means you only allow 1 attempt. So this is a quick revision. Then we look at question number 11. Which 2 of the following statements are true of a distance relay? So we're still continuing with distance relays. It has a straight line. The distance relay has settings in terms of hooks and ends. This is a repeat question. Okay. It has voltage and current inputs. It may have a mode, offset mode, or quad characteristic. Actually, it's a repeat question. So hopefully you get it correct now. I give you a long time here. So I repeat, does it have a straight line characteristic? Okay. Does it have settings in terms of hooks and ends? Or it has, okay, this question time's up almost. So the answer I wanted was number 3 and number 4. Some of you give wrong answer, unfortunately. Okay, so it doesn't have a straight line characteristic. Either it's a quad, so a quad is not a straight line, or it's a circle. So, okay, next one. Why is it not moving? Okay, let's try again. Question 12. Which 2 of the following statements are true of a distance relay in the TMB system? TMB SCB. SCB is about solar energy. Zone 1 is a main protection. Do we use zone 1 as the main protection when in TMB SCB system? Assuming that, of course, you've got a current differential. Zone 1 is activated only if there is a comms link failure. Okay, zone 1 can trip for faults within 100% of the line. And zone 2 is a backup protection and can trip for a downstream busbar fault. So some of it is a repeat. Okay, so what are the answers that we are looking for? And the answers are number 2 and number 4. Okay, zone 1 is a main protection. Zone 1 is not in use. Okay, that's why. So current diff, when your current diff, main one is in use. Although it's there, it's not used. So the answer number 2 is correct. And zone 1 can trip for faults within 100%. Zone 1 is the under-reaching protection. It only trip for faults within 80% of the line. Okay. Okay. Hey, I see a new CCY and Apple. Okay. Okay, number 13. Okay, which of the following statement is true of busbar protection used in transmission substations? A protection scheme for a single bus. Okay, I didn't on my receiver. Okay, so I cannot read. Okay, the second one says that 1 out of 2 tripping arrangement. A low impedance relay is cheaper. Okay. Both the low and high impedance bus schemes have checked. I don't. Okay. Time's up. So the answer I wanted is the last one. Both the low and high impedance have checked relays, I think. Oh, a lot of people answer number 1. I don't know what the full question is. Why? What's the full question? About busbar protection. Somehow what I see on my screen here is slightly. Why there so many people give? Anybody can tell me what's the first answer? A protection scheme for a single bus substation with a bus section. Anybody can tell me why so many people get it wrong?
Mr. Lee, low impedance ada check zone nggak? I think don't have check zone lah.
Yeah. They have their check zone. Otherwise, how do you know where the fault is? I mean, how do you internally there's a check zone? Yes. Okay, I don't know what the question is. Sorry. Okay. If you want to confirm, I can do that. Okay, let me do this question and we confirm now. The fastest protection following the failure of the busbar protection during a 122 kV fault in a H substation with 2 parallel. So what's the fastest protection? Is it the breaker failure? There's a failure of the busbar protection. So is it the breaker failure? Is it the overcurrent relay? Is it the zone 2 and then zone 2 again, or the bus separation scheme? And the answer is, hey, how come I got the wrong answer? The fastest protection. I think I also got the wrong answer here. Sorry. The fastest protection should be the breaker failure. What did I put in? Remember the breaker failure had a faster time, so somehow I put the wrong answer. So it should be the breaker failure. My apologies.
This is busbar protection relay fail, right?
It doesn't matter. As long as the sorry. Correct. What by correct. Sorry, Win corrected my correction. So Win is right. The last answer is correct. It's a busbar protection fail, not the breaker fail. So the answer is correct. It should be the bus separation scheme. Okay. Today is not a good day. Okay. So CCY. Oh, now X. Oh, Win Xiao, you're doing well. Thank you. MY, KO. Okay. Okay, let's look at question 15. I think we got another 4 more questions to go. Which two of the following statements are true of a 275 kV substation with the H arrangement with 5 circuit breakers? How many 50 BF relay? How many breaker failure relays are there? Is it 5? Okay. There will be a total of 3 bus separation scheme. Is it true? 3 bus separation scheme relays. Each line will have 1 current differential relay. 275 kV. Do we have 1 current differential relay, or is it more than that? The breaker failure relay will initiate a tripping of a minimum of, I think, 3 breakers. So, time's up. And the answer is number 1 and number 4. There will be a total of 5 breaker failure relays. And number 4, the breaker failure relay will initiate the tripping of minimum of, I think, 3 breakers. Some of you gave that each line will have only 1 current differential. At 275 kV, each line will have 2 current differential relays. Okay, number 16. Okay, what is the condition required for the pickup of a breaker failure relay? So when you say I want one answer, so the first 2 answers are almost the same, but they're not. So the first one is either overcurrent, the current is higher than the setting, or associated breaker fail. The second one is current is higher and associated breaker fail. The third one is after the relay had tripped. And the fourth one is the protection relay had failed. So I want one answer. So the first 2, be careful. One is or condition, one is the and condition. So the answer is number 2. It must be 2 conditions. Breaker, the relay tripped but didn't reset. The fault current is still there, so it's an and condition. So some of you gave wrong answers here. Also the last answer, the protection relay had failed. No, the breaker failure means that the what we got, there was the breaker, the relay tripped, but the relay operated, but the breaker didn't trip. Okay. Oh, still the same people. Huh? Oh, now Kelvin is coming in. Okay. Oh. Okay. I think these are the last 2 questions. Auto reclose is initiated after the operation of the following. Is it operated after the main protection, after the backup protection, after the bus bar protection, or after the breaker failure protection? It's initiated following one of these. Which one will initiate the auto reclose process? Main, backup, bus bar, or breaker failure? Oh, too long a time. Technically, all of you answer, then the question should stop. And the answer is main. If the backup relay operating, something is wrong. We don't know where the fault is. And if the breaker failure operates, we know something is wrong already. So we don't do auto reclose. We only do auto reclose if the relay operated correctly, the breaker operated correctly. Okay. So we are looking at the last question now for this section. So, okay, only one question. Which statement is true of a bus separation scheme for a transmission substation? Okay, its purpose is to split the system by tripping the bus section circuit breaker. It will trip the incomers. It is an instantaneous protection. It is slower than the upstream backup protection. So one answer is what I want. Okay. Oh, 135 already. Okay, and the answer is, oh, a lot of you got correct. Okay, very good. Only one got wrong. Okay, very good. Okay, so that's the end of the session on the first question. So, X, I don't know who is X now. There should be a total of 68, 17, yes, 68 marks. We got 58. Wow, Win Xiao, Win Xiao, you did very well this time. Bowman consistently there. DMY, I don't know who is that. Calvin, last time you were not, I didn't remember seeing your name. So if anybody interested, just go down a little bit. But and you can see your score from your iPad, your device. HH 50, CCY 50, KO. Okay. Then HA, I'm sure I know this name. Arman. Well done, Arman. Fred. Okay. Yeah. Just now, Fred. There was a question by Chom. Maybe you can help out afterwards. PPH. Qua. Okay. The question was, does the low impedance have a check zone? You want to have to answer the question?
Hello, Mr. Lee.
Yeah.
I'm also not very sure because I'm not sure also.
It does have. But okay, if you want, I will find some of the documents. Okay, so Ho, PJH, LY, ALB. Okay, I think anybody. Okay, I'll show next one. KZ, I don't know. It's Zawawi from ETD, I think. Ken, NDT. NDT. I know where you're from. Okay, Sun. Okay, so that finishes the first set of questions. I know we're very late now, but let me go and do the last question. And the last question is on testing. So this will probably take another 15-20 minutes. So, okay, so now you have to log in again as before. Okay, okay, sorry, I got to go here. I got to go to presentation. Okay. So you're logged in using the new code. Okay. Okay. Can you start logging in? The new code, Okay. Hey, how come nobody joined?
It says presentation is not open. Please wait for presenter.
How come? Why? Okay. This is what we did last time, waiting for
B8.
Sorry?
That's OD8, right?
Yeah. Yeah, I look at OD8. This cannot be 0, and it's O. Oh dear. Yeah, I'll try one slide. Still cannot.
No, still the same.
Okay, I'll try. Okay, you see when I go here, I don't know what to do now. Don't remember. Okay, I will try to go in. Still cannot, is it? Still cannot. I don't know why.
Cannot.
Okay, never mind. I'll just go through very quickly. Sorry, I don't know why. But what I did was I added these slides to it, but these slides should not affect it. Okay, I'll just go through it very quickly. So you have to do your own So okay, polarity test is to confirm the polarity mark. Can you all see the what's on the screen?
Yes.
Yes.
Okay. The polarity test is to confirm the polarity markings. So CTs and VTs got polarity markings P1, P2, and so on, of CTs and VTs. Polarity is very important for certain equipment, directional equipment and differential relays. So directional equipment could refer to things like your kilowatt meter, your direction over current, and so on, distance relay. The test equipment are a battery, so you need a DC supply, and you need a DC analog milliammeter. And the result is the movement of the needle. It will move forward or backward for a short while. Okay. The next question is, the magnetizing curve of CT is performed using a single phase variable AC supply. Okay, to measure the exciting voltage and up to the voltage and current up to the CT knee point. Okay. The magnetizing current shows the increase of the exciting current with the exciting voltage, and a high knee point is required for protection CTs to drive the large fault currents. Okay, all transformers should have low magnetizing current. Okay, then a primary injection tests are performed on CTs to prove the CT ratio, prove that the CTs are connected correctly to the right equipment, and the test equipment is a step-up transformer. Okay, so secondary injection tests are performed on relays and meters to calibrate the meters. Okay, check the pickup current value and time delay of relays. Check the bias characteristic, the harmonic characteristic of differential relays, and determine the polar plot of directional relays and distance relays. Okay, and stability tests are required for all differential relays. Most important stability test results. So please remember this in mind. This is going to be a question. The most important result for a stability test is the operating coil current or the spill current. So you will spill current. That's what I want for a stability test result. The others are just for information. End-to-end tests are required for current differential relays. Okay, and this will involve 2 computer control test sets, very expensive test set, with a GPS communication link. Okay, and the possible alternative to the stability test is an on-load measurement when the load is still very small, because you don't want to trip. Okay, so okay, I know you all said you still cannot get it. Never mind. I will start the test. So question 1. So we'll just let it run out. So you still cannot test out, do anything, is it, guys? Arwin? Still cannot, is it?
Let me try one last time.
Cannot.
Huh?
Cannot.
Still cannot. Never mind. So the polarity of CTs and VTs is very important for these 2 equipment. So which 2 equipment? All differential relays, overcurrent relays, breaker failure relays, power and energy meters, and ammeters. So what's the answer? We can discuss the answer. Okay, now we run short of time already. Never mind. So what's the answer? The answer, of course, nobody answered. So all differential relays, right? Because differential relay got direction. One's coming in, one current goes out. Overcurrent relays, we're not interested. Breaker failure, not interested. But because the power and energy meters. Power and energy got direction, whether power is coming in or going out. So you import, you export, you have to use different meters. And of course, the last answer, ammeter, is not correct. So the 2 answers are differential relays and power energy meters. Okay. Question 2. Okay. The polarity test of CT requires the following equipment. Okay, tell me which is the answer. Okay, Win, you start. Tell me which is the answer. Is it AC test supply? Is it a battery? Is it AC voltmeter, DC voltmeter, AC voltmeter, a DC AC ammeter? Okay, Win.
Battery and DC.
Battery. And the answers are battery and the DC ammeter. Because polarity, we use a battery. Okay, so let's see whether Win is correct. Next one, Agong, you get ready. Okay, so the answers are number 2, battery and DC. Okay, Agong, you're the next one, huh? Okay, leaderboard, obviously nobody lah. So question 3. Okay, the magnetizing characteristic, Agong, for a CT is performed using the following 2 equipment. Okay, after this, Chong, a fixed voltage, a variable voltage, a three-phase supply, a single-phase supply. So Chong, get ready for the next one. After that, who? Jeffrey. After that, Jeffrey Teo. Jeffrey Tay. Sorry, what am I talking about? Jeffrey, after this, you get ready. So Chong is getting ready for the next one. So the answer, how is the test carried out? So the test carried out using a variable voltage, because you're going to increase the voltage to the variable voltage, and the single phase. You're going to test one CT at a time. So okay. Chung, will you be ready? Okay, question 4.
Yes.
Okay. Jeffrey Tay, you get ready for the following one. The polarity test of a CT is performed using a DC ammeter and a battery. So what's the purpose? To test its ratio, check its P1, P2, S1, S2 markings. Okay, check its accuracy, check it is connected correctly. So Chung, which is the answer?
Number 2. Check that
Number
P1,
2.
P2 and S1.
Check the polarity markings are correct. Okay, Jeffrey Tay, you get ready, Okay, and see number 2 is correct. Okay, next one. Agong, just now you didn't answer, so I'm going to throw the question back to you. Okay. So Agong, Jeffrey Tay, are you ready, Jeffrey? Oh, no, Jeffrey is not available. Win Xiao, you want to act as a backup?
Oh, sorry, I didn't click.
Okay, the primary injection test is performed with the following 2 objectives. Prove that the CTs have the correct ratio, primary injection. Test that the relays are working properly. Prove that the CTs are connected to the right equipment. Check the knee point and check the operation time of the relay. So
1 and 3.
Oh, 1 and 3. Let's see. Okay, and the answer is 1 is correct. It's actually 1 and 3 correct. Okay. Oh, thanks. Okay. Okay. Who else? Okay. Kuah Siapo, get ready. Okay. Are you with us, Kuah Siapo?
Yep.
Okay. Get ready. After that, Ong.
This is mine.
This is yours. Okay. The secondary injection test should be very easy on an Okan relay is to number 1, check its pickup current, check its ratio, confirm it is properly connected, confirm it is stable, perform a timing test. Should be very easy 1
and 3.
1 and 3.
1 and 5.
1 and 5. It's 1 and 5. That is to check the pickup current and also to perform a timing test. Yes. How accurate. And you can see the answer is 1 and 5. Okay, Ong. Get ready. Hey, who was the one that? Okay. Okay, Ong. Okay, Ong, get ready for the next one. Who else can I get? Agong, you're not with us, is it?
Yeah, I'm with you.
Okay, you get ready for the next one. This not yours, the next one after this. Okay, the stability test is performed on the following 2 equipment. So which 2 equipment need stability test? Distance relay, thermal overload, restrictor fault, current differential, and frequency. Ong, which one? Oh, Ong not with us.
Looks like Ong have left.
Ong is left. Okay, anybody want to try this?
Okay, let me.
3 and 4.
Number 3 and 4. Who was that, by the way? Who was the one that answered? Okay, and the answer is correct. It's 3 and 4. Restrictor 4 relay is a differential relay. Current differential is a differential relay. So, okay, Agong is the next one. After Agong. After Agong is Hyang. Okay.
Yep. Okay.
Sorry. Same one. Okay, number 8. I think there are only 10 questions for this one. The stability test performed on the following two protection. Okay, it's more or less a repeat, but now it's a slightly different set of answers. Transformer differential relay, current differential is a repeat at some part of it. Overcurrent, standby fault, distance relay. Should be very easy, Agong.
1 and 2.
1 and 2. Okay, Hyang, you get ready for the next one, huh? Hyang, are you with us, Hyang? If Hyang is not with us, then call from PromServe. I know who LMY is. Li Mingyuan. Okay, 1 and 2. So those are the two. So either Hyang or Li Mingyuan, either one. Okay, last 2 questions really. Okay. Hyang, are you with us? Or call from PromServe?
Yeah.
Okay, who's that? Okay. The most important result of a stability test this is very easy. What's the most important test result of a stability test? Operating coil or spill current, primary current, CT secondary current, bias operating coil current.
The operating coil or spill current.
The number 1, operating coil or spill current. Thank you. Okay, last one. Zawavi, you want to try this? Zawavi from ETD. Okay, stability test or transformer differential protection can be checked using the following 2 methods. Zawawi, are you going to try this? Measuring the operating coil current during on-load measurement, simulating an internal fault, simulating an external fault, by measuring the bias coil current, by carrying out a timing test. Okay, Zawabi, are you with us? If not, anybody want to try? Agong, you want to try?
Simulating internal fault.
2 and 3.
Internal fault. Okay, I hear answer.
External fault.
External, is that Munira, right?
Yes.
Okay, it's an external fault. Because stable means external, fault is outside, you don't want the relay to trip. Chong, I think you say 1 and 3, right? So yes, the answer is 1 and 3. By measuring the operating coil current during on-load test or by carrying out an external fault.